Hello, everyone. Today is March 21st, 2022. Thank you all for joining us for the Energy Storage Enhancements meeting for the revised straw proposal. My name is Brenda Corona, here with the Stakeholder Affairs Group at the California ISO. Today, I will help facilitate today's meeting. I'm also joined by George Angelides and Gabe Mortov from the California ISO. Today, we have a few meeting reminders to present to you prior to the beginning of this meeting. Is that this information is located in the Stakeholder Initiatives page under the Energy Storage Enhancement, as well as this reminder that this meeting is being recorded, and the video file will be posted publicly available under the ISO Stakeholders Initiatives webpage. So any related transcriptions should not be reprinted without the ISO's permission. These calls are structured to stimulate dialogue and engage different perspectives, so please keep comments brief, professional, and respectful. We will pause at moments during the time of this meeting. I will make sure if you do raise your hand, we will call on you and unmute you. Once your question is asked, please first state your name and affiliation before making your comment. After you're done, please put your hand down in order for us to go to other attendees who are asking questions. For today's agenda, we will have Gabe present one slide with the changes to the straw proposal. And then next, we will have an energy storage resource model presented by George and Gabe, and then Gabe will present the majority of the presentation with the power mitigation, market power mitigation, and reliability enhancement. And then lastly, the co-located enhancements. And then I'll go ahead and end the meeting with our next steps. At this slide, we are currently in the beginning of the proposal development where we're presenting the revised straw proposal. Our next step is to go ahead and get comments and then also proceed to the draft final proposal. And then this is a timeline of how we are now today. So we have a meeting and then the comments due in approximately a week and a half on Monday. And then our plan is to do a draft final proposal in May, as well as a follow-up for the July final proposal meeting. And there's a likely chance that the Board of Governors meeting will take place around September 2022. Now I'll go ahead and hand it off to Gabe to present this slide.
Thank you, Brenda, and good afternoon, everybody who's able to join us. Thank you on the phone lines for being here. We appreciate it, and we've certainly appreciated all the feedback and the input we've gotten on this initiative so far. I think it's been really helpful in instructing where we're going and how we're thinking about storage resources and the new tools that we're hoping to implement through this initiative. Brenda, as she noted, will be maintaining the questions that we get on the call line, and in the event that we have additional questions that we're unable to get to, you're certainly welcome to send that either to Brenda or myself, and we can try to address those questions as best as possible. This slide is certainly not an exhaustive list of everything we've changed in the revised straw proposal from the straw proposal, but it does cover sort of the highest level elements that we made changes to. And I think that these are important, and what I'd like to do with the time that we have today, which is 3 hours, is spend most of our day thinking about these particular items, and hopefully, we won't be spending as much time going over some of the stuff that we covered last time that hasn't changed as much. Obviously, if we have extra time, we're happy to take questions on, what we presented last time and what hasn't changed. And this is still just a revised straw proposal, so we're not quite to the final proposal stage yet, so there still can be changes to the proposal. We are listening to feedback, and we want to stay engaged and involved. So as we get that feedback, we will be thinking critically about it and internalizing it as we go forward. The other thing I would just like to note is Brenda outlined the topics that we're going to be discussing today, and I want to stick to having comments just on those topics. So if you've got a question and it's about something that's coming up later in the agenda, if you could hold those questions until we get there, I think that would be best. And then, we can talk about questions after we've covered the content that we have in the slide deck. With that, we do have quite a few slides, and I would hope and I would like to get through everything that we have today so that we can fully present on our thoughts and ideas here in this revised straw proposal. So a lot of the comments, and I think this is true of a lot of straw proposals the ISO put out, focused around including additional examples and additional clarification on how specific features that we were proposing were going to work in practice. And I think, I hope what we've done with our paper is really to expand in those particular areas, and that's certainly what we spent the most time and we had the most focus on as we were working on developing this revised straw proposal. One of the specific things we're going to do, and I think George is going to tee up the topic of ESRs, but I'll run through some of the specific examples that we had on the ESR bidding and how dispatch instructions will work for these resources, and those were also included in the paper. So we do spend and will spend quite a bit of time on that today. We've also thought a little bit more about market power mitigation for the ESR resources, and I think we had sort of a note in the initial straw proposal that market power mitigation would apply to the ESR resources, but we didn't necessarily have all the details worked out and the specifics on how market power mitigation would actually be handled for those resources. In this paper, we've tried to flush those details out, and obviously, this could be one of the things that we spend a fair amount of time talking about today, and we will be internalizing it, iterating on this in between this revised straw proposal and our draft final proposal that we're hoping to put out in a few months. We had some questions from stakeholders about details and specific examples for how compensation would work for exceptional dispatches for storage resources that we're told to go and hold a specific state of charge. This is a new functionality that we're planning to introduce for storage resources. Today, we don't really have this concept, but it would be new. And I think the question that was still open after the initial straw proposal was how specifically this is going to be implemented. And here, again, similar to some of these other topics, we've included some additional examples, and we put pen to paper on a little bit more of the details on how we see that compensation piece working for those kinds of exceptional dispatches. We've also, we got a lot of feedback in the last iteration of the paper on co-located resources, and I've actually already fielded a few emails from stakeholders on treatment of co-located resources today and how that might change or might need to change into the future. I do think we've really thought hard about this, and we want to be able to make the right accommodations for resources, and maybe we haven't gotten there yet. Obviously, we can talk about this later on in the presentation, but where we're at right now is, I would say, significantly different in terms of what kinds of resources can apply and be awarded these kinds of accommodations. So there has been some movement on this. Obviously, as we continue to develop and iterate on this specific initiative, we can continue to think about what the needs are for storage resources and developers and operators, and we might continue to iterate on this as we move forward. Just to kind of summarize where we are, though, is, we understand that these contracts that some storage resources may prohibit certain operations, and typically the ISO models physical capabilities for resources. I think we are willing to make allowances for these resources because a lot of these contracts were struck before the market mechanisms to actually operate the resources were put in place, before we even had much in the way of storage on the system, and even necessarily developed models in our markets to track and maintain state of charge. So I think we're willing to do that, and I think we're going to continue the dialogue on what the needs of the resources are. But with that said, we're also thinking about a specific time frame, and right now we're thinking about just a 5-year period for this. Okay, I don't want to get into too many details here, but we will go into these details more in the last section of the paper, which I think will be coming up at around 3:20. Okay, so with that, I'm going to turn it over to George, who's going to do the introduction to the ESR model and explain a little bit about how it's going to work in our systems. And then I will do, walk through some of those bidding examples for those resources. So George, I'll turn it over to you, and we can advance the next slide.
Thank you, Gabe. Good afternoon, everybody. This is George Angelidis with the ISO. Let's have the next slide, please. So before we're going to outline here the new energy storage resource model. Let's talk a little bit about what we have today in production. We're using the non-generator resource model today. It's a general purpose linear model for a resource that can both provide energy to the grid or absorb energy from the grid. And it's used for several different applications, one of them being to provide a model for limited energy storage resources. It's also used for demand response and some other generic applications. Specifically for the limited energy storage resource type of the NGR, the model allows storage resources to participate in the energy and the ancillary services markets. It does support for charging efficiency. We also call that round-trip efficiency. And of course, it has a full list of state of charge constraints that are enforced to make sure that the dispatch of the resource is feasible with respect to the energy that is stored inside. And it has a specific model application for regulation energy management, which is a mode of operation where a storage resource provides regulation to the grid and only regulation as the only service, with having basically no energy bid. We keep that resource as much as possible at 0 megawatts. It only moves around 0 megawatts if it is to provide regulation, if it is to replenish its state of charge so that it can continue to provide regulation. So that's a very specific application of the NGR model for that. Regarding the level of participation, it's pretty similar to all other traditional resources where bids are submitted from a charging maximum capacity to a discharging maximum capacity. It's a continuous bid. It's a function of megawatt, like all other incremental costs in the system. And we schedule and dispatch the resource in the market based on the locational marginal prices and what bid is submitted. Let's go to the next slide and have a graphic here to illustrate how this model works. This is the classical energy bid that you expect from a limited energy storage resource model under this NGR. As I mentioned, it's a continuous model. There is no discontinuity around 0. The only thing that separates the operation of the resource from charging to discharging is that the charging portion has an efficiency that could potentially be less than 100%, and that's why we use a binary variable to separate the operation between charging and discharging for these resources to make sure that we properly capture the fact that the energy that is used to be stored in the device during charging, and not all of it can become available to be discharged because of that efficiency. This model has served the ISO and the participants for a long time, but we have come to realize from the various comments and discussions that we have had in stakeholder forums and in exchanges with participants that it has some shortcomings, and some of them are because of the fact that this is a model designed for very general participation of a linear resource. It doesn't capture some very specific characteristics that you expect to find in storage resources. Specifically, the cost for operating the resource is really dependent on the state of charge that is in the device, particularly when it operates near empty status. When the state of charge is depleted, it's higher to operate the cost. There are additional wear and tear costs that this particular energy bit doesn't capture because it's a function of megawatts. And also, most storage resources, they have very high ramp rate. So having an energy bit that varies with respect to megawatts is not very useful, since really when the resource is in the money is dispatched at Pmax or at the highest economic limit that is submitted on the bid. You don't have much variation in between. So it's not very useful to represent the cost of the resource in terms of megawatts. There are some other limitations with respect to the upper economic limit or the operating limit of the resource being also dependent on the state of charge and even the ramp rate that I mentioned earlier. Although it's a great ramp for most of the operation of the resource, when you try to operate the device near full charge or near its depleted status, really the ramp rate is reduced. So to provide a better model that captures the specific characteristics of storage resources, we proposed here a new model. We call it the Energy Storage Resource Model. Can I have a next slide, please? And what we're doing with this new model is a different representation of its costs. So we represent the incremental cost for operating the device in terms of its state of charge instead of in terms of its megawatt output. And to be able to separate the cost of operation for charging and discharging, what we propose is to have two different sets of bids, of incremental cost bids with respect to the state of charge, one for charging and one for discharging. And we'll make sure that the total number of segments on those bids is limited to 10, like every other resource, so that we have the same playing field. And also we introduce some dynamic variability of the upper and lower capacity limits for the device, also as a function of the state of charge. This slide says here register step function. It will actually be a linear function. We'll have some example to illustrate that. And similarly, the ramp rate for regular resources is the function of megawatt output. Again, we're switching everything to be a function of a state of charge for this new model. So we'll support dynamic ramp rates as a function of the state of charge. And with all this introduction, because we already have a separation of the charging and discharging states, now they also have different bids, as mentioned in the first bullet, we are able to model the transition between charging and discharging state, since we already have a binary variable for that, as we mentioned in the NGR model, which we will maintain here. And we'll leverage that functionality to actually model transition costs. So if there is a cost for transitioning the device from charging to discharging, now we can reflect that in the market, and we can also enforce transition times. So if there is a certain amount of time that is required for the transition to happen, if it's not instantaneous, then we can also introduce this transition time in the market to be incorporated in the optimal schedule and dispatch. Let's go to the next slide, please. So this is just a picture to illustrate the bids, the SOC incremental bids that we talked about before and how they're going to work. So as we mentioned, there will be two distinct incremental state of charge bids that will reflect the cost for operating the device. One for charging that's shown in blue here, and one for discharging is shown in red. So these cover the state of charge range of the resource from a low to a high. And you have the opportunity now with this model to separate the cost for operating the device while charging with the cost while discharging. And as you can see, if you're near the low state of charge, when the device is nearly depleted, you have a higher cost of charging and a higher cost of discharging. The charging bid looks like a demand bid, so it's monotonically decreasing if you look at the arrow from low to high SOC, and the discharging bid is monotonically increasing, moving the other way from high to low state of charge. The integral under this bid is the cost of operation. That's what's reflected in the objective function. When the resource is charging, that's the blue shaded area, and that's a negative cost in the objective function because it's demand, so we call it a benefit. And then when it's discharging, the red shaded area is the cost of operating. And we show here that it's possible to charge the resource from T-1 to T, and then at T to transition, and then discharge the device from T to T+1. So this is the mechanics of how the model operates to capture the cost of the resource and optimally schedule it in the time horizon of the market. Similar to the difference that you have between the charging and the discharging bid in the NGR model, there is also a similar gap here, which we call the bid spread. And this is important for the market because the resource is scheduled across intervals to capture that bid spread. So it can charge at the bid cost and discharge, capturing with the LMPs at least that bid spread. So that drives the economic operation of the device across intervals. Let's go to the next slide. So just to illustrate how we will model the dynamic capacity limits that we mentioned earlier. Normally, resources operate from a Pmin to a Pmax, but for this energy storage resource, we will implement some functionality to reflect to the market that when you're near the edge of the state of charge limits, the higher the low, the operating capacity of the resource is reduced. So when you're near the state of charge, when the resource is almost depleted, obviously the upper capacity limit is reduced, so the resource is not capable of producing the same number of megawatts. So that is shown here with a blue curve. And also, if the resource is charging and you're building charge on it, as you approach the maximum charge that the device can hold, again, you cannot charge at the same rate. You have a lower amount of megawatts to be absorbed. So we'll set this up in the master file with those parameters A and B so that scheduling coordinator can capture the more detailed characteristics of the capacity limit as it varies with the state of charge. And similar to this, we'll also register in the master file ramp rates so that in a similar way you can reflect with multiple ramp rate segments that on the resources close to those SOC limits, the ramp rate of the resource is reduced. It's not the regular ramp rate that you have in the remainder of the operating range in the state of charge. Let's go to the next slide. And let's pause here for some questions before I hand over to Gabe to start working with some examples.
We can call on Carrie Bentley for Western Power Trading Forum. Let's go ahead and unmute her for her question.
Hi, George. This is Carrie Bentley from the Western Power Trading Forum. I have a high-level question, but I could save that till the end. My detailed question, can you go back a couple slides where you have the table that explains, one more forward. Nope, where you're explaining the model, the one that has the bid curves on it. Yeah, that one, perfect. The way I'm interpreting this is that you're gonna have the bid spread the same at all state of charge levels. Is that correct?
Oh, no.
The bid spread here just confuses me the way it's articulated.
Yeah, and it's, maybe I shouldn't have included it, but essentially what this says is that if you have the highest of your charging and the lowest of your discharging bid, what I show here that there's a gap between those, and that's what is the bid spread. This is the healthy way to capture the cost, and that's why I'm putting it out there as a suggestion. Because if these curves overlap, that is, you don't have a bid spread, but you have some part of the discharging price to be lower than the charging price, you may create some scenario where the market will try to charge and discharge in the inverse way. Usually you want to have a clear price separation between the charging operation and the discharging operation. So that's why I put it in. It's more of a detail.
I see. Thank you.
We will not validate.
You're not going to validate that, though. Okay, that's helpful. And
No.
I have to admit, I didn't see that last blue line. It was just very light. But now that I'm looking at it closer, I do see that it's a difference between the highest charge and the lowest one. But okay, that makes sense to me. It's just indicative of a kind of more of a correct bid rather than something you'll validate.
Right.
Okay, thanks, George.
You're welcome.
We have a question from Alva Savoda from Pacific Gas and Electric. Let's go ahead and unmute him.
Hello, George. This is Alva.
Hi, Alva.
Thanks so much for these detailed examples and a lot more richness to your description of the model here. So thank you very much for that. The ramp rates, I was wondering, I think to date, ramp rates have always been the same, whether upward or downward. I mean, within a particular range at least. Is this model one where, because I think the actual constraints are not, they're not bidirectional ramp rates. The ramp rates are decreased in one direction or the other differently. Are you going to, like if the ramp rate goes down close to full charge, are you going to restrict the ramp rate in both charging and discharge directions? Or will you, will they differ?
Yeah, so let's break this down a little bit. So you're correct. Today, our dynamic ramp rate model has the same ramp for ramping up and the same ramp for ramping down in terms of megawatts. Now, the ramp rate may change at different levels of megawatt schedule or megawatt dispatch. But for going up or down, if you're in the same segment, it's the same ramp rate. And the same principle applies here, but the ramp rate function is a function of the state of charge instead of the megawatts. But if you're on the same segment of the state of charge, it doesn't matter whether the state of charge is increasing, in which case you're charging, or decreasing, in which case is discharging, still the same ramp rate. but we wanted to provide the ability to reflect a reduced ramp rate when the resource is nearly fully charged or nearly fully discharged.
Right. So if you're like near full discharge, let's say, so you basically really want to charge, and you have a relatively small segment at near full discharge, where you're constraining the ramp rate within like an. I'm mostly interested in this model in the day-ahead time frame in terms of how you combine the, and I think you showed it very well here, kind of like how you might be combining different segments of the bid curve depending on what your state of charge is over the course of an hour. So what you're saying that the ramp rate that's used could vary within an hour for depending on the direction you're moving, for example, that you could move out of that low ramp rate segment into a higher ramp rate segment, and then the higher ramp rate would get used within the hour. Is that correct?
It's difficult to say that obviously this figure because this is not a ramp rate figure. But
maybe the next slide, I think you showed it on the next slide.
The next slide shows the capacity too,
okay.
Instead of the ramp. But
Yeah.
let's, and I had a slide that had the ramp rate curve, I just didn't include it here. I thought it was too complicated. And maybe I can search to find it, but let's consider a scenario where you're charging the device. So you're building a state of charge, and it has, let's say, a ramp rate of 40 megawatts per minute. And when you reach, let's say that you can charge the device all the way to 100%, okay? But when you reach 95% on the SoC, now the device absorbs energy at a lower rate because it's almost full, right? So if you want to capture that in the ramp constraints, then we have a ramp rate that basically for the, let's say, for the that last 5% state of charge to get it full, the ramp rate is reduced from 40 megawatts per minute to say 5 megawatts per minute. So it's a dynamic ramp rate, the same way like we use for other resources, but instead of being in terms of megawatts, is in terms of the SoC.
Right, but if you were suppose you're at 98% and you want to discharge, so that ramp rate only applies for 5% of the capability. I have to come up with an example, but basically, suppose that it only takes 10 minutes to get out of that state of charge interval. The remaining 50 minutes, you should be using a much higher ramp rate. Will the model take some kind of an average, or how is it going to calculate the ramp rate on the discharge side in the example you just brought up?
So it's like taking an average because it enforces the constraint across intervals, intertemporal constraints. So it calculates from the previous state of charge going to the next state of charge, what's the rate of change in the state of charge, and then it limits that to what is defined as the ramp rate for state of charge. Let me ask if Brenda, can you make me a presenter for a moment? I can share a slide that has a figure that shows the ramp rate function. And then we can come back to the presentation. Is that even possible?
You should be presenter now. Go ahead, George.
Okay, let me try to do that. So, okay, let me see. So bear with me, Alva, for a moment.
Thanks, I appreciate your.
Yeah, I was not ready to show this slide. Of course, I'm also showing here the equation. Just forget the equation. This is just the dynamic ramp rate. But if you see the figures, Now, you have a ramp rate function that instead of being defined, and it's still segments, right? It's still a step curve, right? But instead of being defined in terms of megawatt output, the horizontal axis is megawatt hours, and that's your SOC, right? So it says here from 0 to 20 megawatts. So it's when you're low on the SOC, the ramp rate is 12 megawatts per minute. And it's also 12 megawatts per minute from 80 to 100, right? This is the characteristic we want to capture, that, you have a high ramp rate for SOC between 20 and 80, but it reduces to a smaller amount when you're near fully charged or fully discharged. So that's the ramp rate, the way it's defined in the master file. What the application does, and what it does similar to other dynamic ramp rate curves, it calculates the ramp rate capability. And this red curve below shows your 5-minute ramp-up capability. You calculate a ramp-up capability and a ramp-down capability. They could be different, right? Because you go through different segments. So as you can see very quickly here, because we don't want to spend too much time on this, from 0 to 15, you basically have your 12 megawatt per minute ramp rate. So your ramp-up capability is 5 megawatts. For any 5-minute interval. And then when you hit 20, you go to the 24 megawatts per minute, so now you can ramp up 10 megawatts. So between 15 and 20, that's where your average comes in. You have a linear segment because now you're crossing from the 12 to the 24 in the same interval. So essentially your ramp-up capability changes as your SOC moves from 15 to 20. Then it stays at 10 megawatt, your ramp-up capability, because you're on the 24 megawatt segment, et cetera, et cetera, et cetera. And that's how the application builds this function. And then with binary variables, it enforces it in the optimization for every interval, depending on where the SOC is, because the SOC is actually a variable, right? It changes as we dispatch the resource.
Now, the one thing you said which concerns me is when you said for every interval, in the day ahead where the intervals are hours, it's clear that you have several. You especially in these small segments, you would have multiple ramp rates that would apply within the hour. Am I correct?
Yes.
Capture that? When you said interval,
yes,
you mean like an hour.
Yeah, I meant the interval in the application. So of course I was building this for 5 minutes in the RTD. It will be 60 minutes in the day ahead. But if you go to the day ahead, the 60 minutes is such a big time interval that you'll find that most of the time you end up having a ramp-up capability that says you can move the device all the way to its Pmax within 1 hour, right? And because even if you have a small ramp capability, over 60 minutes, you're going to transcend all of this. So what happens is that for fast ramping resources like these ones, the ramp capability constraint doesn't factor that much in the day-ahead market. It's not very limiting. You'll see more of its effect in the real time. So that's why I built this example for real time.
Right.
But it could happen.
It's not very limiting, but it is limiting, right? I mean, in other words, if you're at 100%, you have to get from 100 to 95 first, and then you can have a faster ramp rate for the rest of the hour, right? So that would be in the model.
Yeah, it's the same model, but with 60-minute ramp capability. So if it's binding, it will show up. So I'm going to stop sharing this.
Okay, that's great for now. I don't want to pursue it any further, but thank you very much, George. Appreciate it.
You're welcome.
We do have a question from Stefan. If you like to ask your question.
Hi, this is Steve Keene from Pacific Energy Enterprises, Pacific Energy Advisors. I'm getting confused here between you talk about the ramp rate for a storage facility, and I'm not sure if you mean the ramp rate or the charge rate. Ramp rate, I think about ramp rate like...
It is the charge rate and the discharge rate. So the ramp rate as a function of the state of charge is really the discharge rate and the charge rate.
Okay. that might make more sense and make it a little cleaner, because when I think of the ramp rate, I'm thinking about that storage unit, it was charging at 10 megawatts an hour, and then you move it up to charging at 20 megawatts an hour. That, whether it can do that. Because when you talk about the ramp rate for a generator, it's how much it can move, right, within a period of time, not how much it's charging or discharging.
You're correct, yeah. Now, because everything is reflected here as a function of state of charge, really the ramp rate is really a charging or a discharging ramp rate. Yeah.
Okay, but isn't there still, there would be that, but so like as long as you're within one of those segments on the curve, on the other example, then basically you can essentially go down, but you can't go up. If you're on the discharge piece and you're discharging at what the unit can do, they could conceivably reduce that, but they couldn't go up until you hit that next segment where you may be able to have a slightly different discharge rate.
Yeah, that's why I mentioned to Alva that we calculate a ramp up and a ramp down capability. So that will be discharge rate and charge rate at every point on the state of charge. And if you're in the same segment of the ramp rate, you may have different discharge and different charge rate over the 5-minute or 15-minute or 60-minute, whatever the interval is, because it depends on how many ramp segments you're going to go through in that interval, right? So.
Right. Okay, then I have one other question, and this is just because I'm not familiar with the way storage units really operate. I would think that when they were at a low state of charge, you could put more in. You're seeming to show that the charge rate is low both when they're full and when they're empty. Is that a function?
Yeah, from the comments and the discussion that we had with storage participants, the understanding that we have is that when the device is nearly fully charged, you can still charge it, but at a lower rate. So it's more difficult to charge it. At that point, it absorbs energy slower than before. So it has a lower charge rate. And also, its megawatt absorption is also reduced. So if you have a plus minus 10 megawatt device, you can charge it at minus 10 megawatts, but when you start hitting its very high state of charge levels, the device is operating at a reduced charge megawatts, let's say minus 8, and also a reduced rate. So it becomes more difficult to charge it at 100%. It's like the battery in your laptop that, it charges quickly up to 90% and then it's very slowly to get it to 100%.
I understand that. What I'm talking about is the flip side of that. So when the charge is very low, does it also have a low charge rate?
Yes.
That's what you were showing in your examples.
Yes, that's also true on the other end of the spectrum. When you're discharging a battery, when you are depleting its charge and you're reaching to the empty state, again, the rate that you're getting the energy out of the device is reduced, and the megawatts that it can be dispatched is also reduced.
No,
right?
And that makes sense to me. What I'm looking at is is that symmetrical on both sides for both charge and discharge, or is that a one-way phenomenon? So when the battery is very close to being fully discharged, does that affect only the discharge rate, or does it affect both the discharge and the charge rate? Because in your examples, it seems you're showing that it's affecting both of those.
Yes. Yes. It affects both of those because we don't model a different rate of charge or discharge at a given state of charge. So similar to our ramp rate model for regular resources in terms of megawatts, if you're at a certain megawatt output, unless you're at the segment breakpoint on the ramp rate curve, you have the same ramp rate for ramping up and ramping down. And the same here, you have the same charge rate or discharge rate at that SOC point. Now, as you change SOC points, moving either up or down, you may change ramp rates. You may go to a new segment. But if you are within a segment, we don't differentiate in the ability of the device to charge or discharge when it comes to the rate of charge or rate of discharge.
Okay, so that's, again, this is where I don't understand the operation of the facilities. But what I hear you saying is that that's a function of the ISO's rules that there can only be one charge discharge rate, not necessarily what the unit can actually do.
Yeah. At a given state of charge, yes. At a different state of charge, you could have a different rate, but the rate for charging and the rate for discharging at that point is the same, yes.
Okay, all right, thank you very much.
And maybe I can provide a little bit of background in this because it may sound weird now that we're saying this. So this is an extension of the same rule we have for regular resources for the ramp rate, that is a function of megawatts. Early on in the MRTU design, we didn't want to have the ability, a resource to ramp up with one ramp rate and then have a different ramp rate for ramping down. One of the reasons was that you could end up having a situation where the resource is in the money and it's ramping up, it's a fast ramp up, and then it's out of the money because, you know, the LMP changes, and then we want to ramp down the resource. But if the ramp down is much more reduced, then the resource is becoming what we call extra marginal, so it's out of the money, and then it incurs costs that are going into the bid cost recovery, and we didn't want to have this asymmetric situation where the resources can ramp up fast when they're in the money, get to some high level of megawatts at some good LMP, and then the LMP drops and the resource gets stuck ramping down and taking a long time to ramp down and carrying a lot of cost for BCR. So that was, you know, the early rule that we wanted to adhere to back in MRTU. And since then, you know, we still have the same model. Now that we're switching this to be a function of the state of charge, we wanted to maintain the same principles.
George, we have one more question. Oh, we actually have three. So just folks, we have 10 minutes for this topic, but we will obviously have more time. So the first person we had was Tong Wu for Western Power Area. Tong, feel free to go ahead and unmute.
Hey, George. I have a question about this big curve. I think I may understand, just one clarification. So here you're saying that for each state of charge, you have a incremental curve and a decremental curve. And
Yes.
The incremental curve is the red one, the decremental curve is the blue one. So this is for each SOC. So I assume these SOC points are continuous. They're not discrete, right?
Yes, it's
okay.
still a continuous model, yeah.
Continuous
the transition
model.
Is the only, the transition is the only discontinuity here.
Okay. It seems the curves are monotonic increasing in terms of the SOCs. So that you will never have a say a higher bid curve for a lower SOC or something. You know, one way to think about is that for each SOC is like also almost like a different unit. You can generate or you can pump, and then at different level you have a different generation or pumping. I know this is not generation pumping. That was the concept I was familiar with. But here you're saying that they have to be monotonic. There's only one curve in discharge. There is only one curve in charge, even though when you pick the SOC point, it's irrelevant for the discharge curve on the left, and it's irrelevant for the charge curve on the right. But nevertheless, you want this curve to be monotonically increasing regardless.
That's correct.
Okay.
This is the fundamental aspect of our optimization model that requires convexity in the energy bids. It doesn't matter whether you represent them as a function of megawatts or as a function of SOC here. The convexity is very important for convergence and for having an outcome where you have consistency between the pricing and the dispatch of the resource. So that's why and it's not anything that you wouldn't expect. I mean, the blue curve is really a demand curve, and that's how demand curve looks like. And the red curve is like a generator curve, and that's how they look like. So we're not really setting different expectations. We're just making sure that we explain that we'll expect that these curves to be submitted like that because that's what you submit for a load and a generator today.
Right. I just wanted clarification, George. So from the discharge and charge, is there any transition time?
Yeah, as I mentioned in the previous slide on this, we have the ability, if there is a transition time, if there's a discontinuity between switching from charging to discharging and vice versa, because we already have a binary variable to separate those states in the model, we are capable now to formally introduce transition time and transition cost in the model.
Okay. All right. Thank you, George. I don't want to take too much
You're
time.
welcome.
I know there are other questions. Thanks.
Thank you.
Thank you, Tong. And we have a question from Brian from Ellis Power. If you'd like to ask your question.
Hi, this is Brian Bartholomew from Rev Renewables. Terribly sorry if I'm misinterpreting this, but just wanted to follow up to Mr. Keen's question and wanted to say that a symmetric ramp rate for the charge and discharge sides does not reflect the physical limits of an asset. A battery that's 100% full, it can't charge at full power, but it can discharge at full power. Conversely, a battery that's empty cannot discharge at full power. It can charge at full power. So if I'm interpreting your answer to that question correctly, using this model would artificially handicap the flexibility of batteries when they're near full or near empty in a way that does not reflect the physical limitations of the assets. So we wouldn't want that because it would make us less able to respond to price signals that KISO is sending. It would deprive KISO of that flexibility when we're near full or near empty. And the assets are physically able to discharge at full power when full and charge at full power when empty. So we'll follow up, but that's definitely something that we'd prefer to see changed.
Thank you very much for your comment, and that's very important. I just want to add that it's not entirely the same capability, it's the same rate. So the rate of charging and the rate of discharging is the same at the same SOC, but as I explained to Alva with that figure that I had on screen earlier, what we calculate is charge capability and a discharge capability. And because in your example, your discharge capability is using the lower ramp rate segment, it's low, whereas the charging capability at the same SOC, it will transition, it will grab a higher ramp segment and it will be a larger amount. So it's not exactly symmetric, right? We're using the ramp rate is symmetric, but the ramp rate capability up and down will be different depending on which ramp rates are used in that interval duration, going up and going down. So we can have perhaps some side discussion on this to explain it. It's a little bit complicated. I try to do it in the figure. It's not so easy to see. But let's leave it at that for now. We can get back at some other time to discuss it more at length.
Okay, thank you a lot.
Lastly, Chris Devon, we could ask his question in the last 2 more minutes that we have.
Hi, this is Chris Devon with Energy Solutions. Can you hear me all right?
Yes.
Yes.
Thanks. Yeah, so I had a similar reaction to Brian in response to your answer to Steve Keen from PEA on the ramp rates. And it just seemed to me that if you're going to have a somewhat similar ramp rate for charging and discharging, it's not really reflecting the physical capabilities, which could then result in some, I think, opposite problems from the way that you described why, the Kaisla set it up that way back in the MRTU days for the thermal resources, which that was very helpful background, George, so thanks for that explanation. But yeah, and also your additional explanation at the end there in response to Brian, too, also helped me realize that it's not going to be exactly symmetrical, but I think maybe a little bit more discussion around this would be helpful because it does seem that it's going to potentially not really reflect how much they could actually discharge, and then have, in the example of, let's say they are dispatched at a high level with the lower ramp rate when they're getting close to their full state of charge, and then they want to, then they get stuck and they want to try to discharge faster, and strand the ability to capture some of those prices. So it seems like there's some incentive there that you're creating that might be a disincentive to get all the way to completely full charge. To sit close inside the range where those ramp rates aren't actually that constrained by those different charging levels. So we can discuss it more. I realize we're running out of time here. So that's just another, echoing that same little bit of concern, and I think some more discussion would be helpful. Thanks.
Absolutely. And if we have any time left at the end of this call, after we cover all the material that Gabe has in his slide deck, perhaps we can come back to it and discuss some more. Yeah, I believe this is the slide that I'm handing over to Gabe. If there are no more questions.
No more questions, but Stephen did raise his hand. If it's something really quick, Stephen, we could go ahead and address it. If not, please both raise your hand. Raise down your hand so we could proceed. We could unmute Stephen. Devin.
Hey, just real quickly, I think I get what you're saying, which is that if we're fully depleted or close to being fully depleted, the charge rate is unlimited. It may be higher because it'll go into that next segment, especially during the day ahead. But I guess one of the questions that comes to my mind then is if we're talking about day ahead on this, where you're talking about scheduling for an hour, what happens if, the charge rate is, 10 megawatts an hour, but there's only 5 megawatts left in the resource? How is that scheduled in? Would they be limited to 5 megawatts, or would they get 10 megawatts, but only for half the period?
Yeah, that's an interesting question. So the application produces a schedule for the interval. You can consider that being the instantaneous schedule at the middle of the interval with the convention that we have. And what the intertemporal constraint for the ramp rate does, it limits the change across intervals. So you have a state of charge in 1 hour and a different state of charge in the next hour. That difference in the state of charge, let's say that the resource is depleting its charge, it's discharging, going from that hour to the next, and the the rate for discharging could be changing in the hour of transition, all right, from the middle of the previous hour to the middle of the next hour. The application calculates what we call the discharge capability over 60 minutes, right? So, and it limits the change in the state of charge between those 2 hours not to exceed that discharge capability. And that discharge capability is calculated based on all the discharge ramp rate that you will hit as you travel from the previous SOC to the next.
Okay. I think I understand that, but I got to think through what the implications of that are. Thank you.
You're welcome. Specifically for the batteries, and if we set aside a little bit what we said earlier about the dynamic capacity limit, because that plays into this, let's say that the Pmax is not affected by the state of charge. If there is no limitation on the discharge rate, you will be able to be dispatched at Pmax going into the next hour, so you're discharging fully. If the state of charge limitation based on that discharge capability becomes binding, then your megawatt will be less than Pmax going into the next hour. It affects your actual schedule. We can probably provide some examples to show that, but I think we should move on now. And I know we had a lot of questions on this ramp rate and the discharge rate. Maybe we can come back to it if we have time at the end of the call. And if need be, we'll probably provide some examples to illustrate this next time.
Thank you, George. We can go ahead and invite back Gabriel to unmute yourself so you could go ahead and proceed with the next slide.
Great. Yeah, I think that was some pretty good discussion, and I appreciate the feedback, and I've been seriously taking notes over here on my end. I did have a few examples to walk through. I think a lot of them are, some of the higher level questions that got asked. As George was saying, I think we could, potentially enhance some of these examples to think about some of the dynamic limits on capacity that these resources might have, to Brian, Chris, and Stephen's comments, and, walk through some of those examples in either the draft final proposal or potentially in another document in between here and that document. But just to move on to some of the examples here, I've just constructed this very easy hypothetical space where you have a resource that's capable, a storage resource that's capable of charging at as low as minus 25 megawatts and discharging at up to 25 megawatts or positive 25 megawatts. So the range of dispatch for this resource is between minus 25 all the way up to positive 25. And then this resource is a 4-hour battery, so it has minimum stated charge at 0 megawatt hours and a maximum stated charge at 100 megawatt hours. And I've just made this a very, very easy example, just to kind of make it easy to walk through. And in this specific case, I've just set a target or a bit curve for the charging portion of the resource at one specific level, specifically $20 per megawatt hour. And then there's a step function for energy discharge. And, sort of the same story that George is walking through. We're looking at 3 different cases. If the resource is near full charge, it's going to be relatively expensive, relatively inexpensive to discharge the resource. If the resource is nearly empty in terms of state of charge, it's going to be relatively expensive to discharge the resource. And if it's somewhere in the middle, you sort of have a middle price, an average price that you'd be willing to discharge the resource at. So if we go on to the next slide, Yeah, exactly. So this is what I'm thinking about here. I'm saying, okay, the resource is willing to charge anytime prices are less than $20 per megawatt hour. If the state of charge is above 80 megawatt hours, then the resource is willing to discharge it's relatively full. The resource is willing to discharge anytime prices are at or above $45 per megawatt hour. If the range of state of charge is between 15 megawatt hours and 80 megawatt hours, I'm willing to discharge anytime prices are at or above $60 per megawatt hour. And then finally, if I have 15 megawatt hours or less of energy, I'm only willing to discharge that. I only have a very little bit left, and I'm only willing to discharge that if prices are, at or above $100 per megawatt hour. So if we go on to the next slide, sort of the first example here, and this is relatively straightforward. Let's suppose we are, we're not in one of those edge cases, and we're not really thinking about the day-ahead market where we could potentially move a long ways in terms of state of charge from one interval to the next. But basically, if we're sitting at 50 megawatt hours or something like that, any one particular dispatch in the 5-minute market is only going to move the state of charge a little bit to the left or a little bit to the right. In these cases, what we're typically going to find in the market is when prices generally are at or above $60 per megawatt hour, you'll see a dispatch instruction issued to the storage resource to discharge energy. If prices are at or below $20 per megawatt hour, you'll typically receive a charging instruction for the resource. And then if prices are in between, so if they're between $20 and $60, then you'll typically get a dispatch instruction to hold state of charge, so don't move to the left or the right. The dispatch is going to be similar to, dispatch instructions that resources receive today, where you would typically see, if prices were, say, $65 per megawatt hour, you'd typically see intervals where you would be dispatched in a way that if the resource did have full ramping capability, you'd see it dispatched for 25 megawatts of energy for discharge. If prices were below that $20 threshold, let's say they were just $10 per megawatt hour, you'd see the resource essentially be getting dispatch instruction to charge at its Pmin, so minus 25 megawatts in this particular case. I don't want to belabor this too much because we are running a little bit over time, but if we go on to the next slide, it's kind of an example. Okay, let's say the resource has 5 megawatt hours. Same type of thing. If prices are above $100 per megawatt hour, you'll get a dispatch instruction to essentially discharge the resource at its Pmax as long as you're not going to exceed the amount of state of charge that the resource actually has charged up. And then if you see, same thing because you've got the same blue discharge bid curve, as long as prices are $20 per megawatt hour or lower, then this resource would be getting typically a dispatch instruction to charge essentially at its Pmin, or minus 25 megawatts. So finally, and I don't think this is a big surprise to anyone if we go on to the next slide, but if the resource has a very high state of charge, we'll be sort of in the same scenario where if prices are relatively low at $45 per megawatt hour or higher, you're getting that discharge instruction. If prices are low, you're getting the charge instruction. I think that might be the last slide that I have. Oh, no, there's one more. Yeah, exactly. So, and I think this is the case that George was getting into, certainly going to be more prevalent when we're thinking about operating storage resources using this model in the day-ahead market. You're going to sometimes be at a point at the beginning of the dispatch instruction where you've got a certain amount of megawatt hours of state of charge, and if you're, in this particular case, if you're discharged a certain amount, you're going to move from the red curve that you're currently on to the red curve to the right where the prices are higher. In the paper, there's actually a typographical error, and we said that the price that would be set on the system would be the average of the two for the dispatch instruction. The actual price is the marginal price. This is the same as we construct in our market today, if this particular resource was scheduled to discharge in a way that the actual state of charge would shift to something below 15 megawatt hours, you'd be in a situation where the marginal price, if this resource was marginal, would be set at $100 per megawatt hour, or you need to see an LMP of above $100 per megawatt hour in order to see that dispatch instruction in the first place. Obviously, the same thing can happen on the other side of the line. If you had, say, 14.5 megawatt hours of energy, there could be a dispatch instruction that could bring the resource just to the left, and the marginal price would then be lower than the marginal price on the right if there was a step in the blue curve, but obviously in this particular case there isn't a step there. And then you've got the same scenario around 80 megawatt hours because we've got 3 steps in this function. So I don't really want to go into, at this point we are a few minutes over, so I don't want to go into more of the details on this example. I would love to see more in the way of written comments, so if you've got specific examples you'd like the ISO to work through, we can certainly include those in our draft final proposal. And I am planning to, certainly include additional details on the ramp rate, which we had just discussed at some length in our conversation with George just a minute ago. So let's go ahead on to the next slide and get into market power mitigation, which is and we can go ahead to the first slide with material here. And this is a bit of a challenging topic, and as I mentioned earlier, this is a situation, this is something that we didn't really get into the details of in the initial straw proposal, and we provided a lot more details on how market power mitigation is going to work in this paper. So I do want to take some time and walk through this just to make sure everybody understands sort of where the ISO is at this point and what we're thinking about. And if we do need to iterate on this idea, we can. So I think the first thing to note is that we did have a lengthy stakeholder process, and we've had sort of an ongoing dialogue with the Market Surveillance Committee, or the MSC, on topics related to market power and market power mitigation and how to calculate default energy bids, and specifically how to do that for storage resources and what some of the key terms were that we needed to think about for storage resources and how these resources may be different than the traditional resources, which we have market power mitigation measures for already. I think the first thing to note would be that a lot of the work that we did on those default energy bids in the first place was in the ESDR 4 initiative, where we were initially coming up with default energy bids for storage resources and under the LESR and non-generator resource models. And those just came into place this year, but they are active, and storage resources today that are on our system are mitigated. So they are subject to market power mitigation. The way that we're calculating those default energy bids for storage resources is 3 separate components. The first component is the cost to buy energy for the storage resources. And I think this is the fundamental way that storage resources are really different than traditional generators. Obviously, for gas generators, you're buying gas, and then you've got a ratio that you can convert gas to electricity, and those costs of buying the gas are an input to the model for how much it actually costs to deliver energy to the grid. For storage resources, this is a little bit of a different principle because they're not actually generating electricity. They're charging energy, taking it off the grid during one interval, and then they're releasing that energy at a later interval. But that cost to charge, that cost to charge the resource is the analogous cost that's used for storage. Hang on just one. Sorry about that. Had a little tickle in my throat there. What we do for storage resources, because we do have multiple runs of our market, we use the first run in the day-ahead market, the day-ahead market mitigation run, and use that as an input to determine what we expect costs to be in our day-ahead market, and then once we use that for calculating default energy bids for storage resources in our day-ahead market. And then once we've completed the day-ahead market, we use finalized results from the day-ahead market to inform or estimate what we think storage resources are purchasing energy for in our real-time market, and use those as inputs to the default energy bid formulations in the real-time market. They're based on the lowest price hours of energy at the location of the storage resource, and they're also based on the duration of the resource. So if you've got a 4-hour resource, you're thinking about the lowest 4 hours of the day, and I believe we've got some language where it's contiguous hours, and you're using those to inform what you would expect the storage resource to pay for the energy that it's charging to be discharged later in the day. And then you've also got cycling costs, which are included. So this is sort of the wear and tear on the resource. So as a typical lithium-ion resource charges and discharges, there is some wear and tear on the metal that's inside of the batteries, and eventually, if that metal is cycled enough times, it will become non-performant and will require cell augmentation, which could effectively be replacing certain areas of the battery with new or upgraded or enhanced components. And that happens after a certain amount of time, and that can be modeled, and it's included in a lot of the warranties and contracts that are struck for new resources that are on our grid. These costs are something that are submitted and verified by the ISO. So once a storage resource is registering for a default energy bid calculation that the ISO will perform, they do have to come to the ISO and justify what kind of costs should be included in cycling costs. And then the other thing that we've done is we know that if a storage for a lot of storage resources, if a storage resource cycles a particular amount, say one cycle per day, then it may have one set of costs around cell augmentation. But if that resource were to say cycle instead of one time per day, maybe 1.5 times per day, those costs could actually be a lot higher. So what we've done, just to be conservative and err on the high side, is to say, well, let's use the upper bound of what those cycling costs are for storage resources. I think the idea here, and again, this is one of the things that we've discussed with the MSC and in previous stakeholders, is that in the long run, we'll probably look a little bit more closely at what these costs actually are, and some of the historical, likely bidding practices of storage resources, and try to better inform what these costs might be for typical resources on a system. And of course, I think a long-term goal would be for the ISO to actually do some of this estimation of, well, is this resource a resource that is cycling more like 1.0 times a day, or is it more like a resource that's cycling 1.5 times a day, and perhaps have something that's dynamic. We're just not there yet right now, though. So we're still planning to kind of stick with the same paradigm that we have essentially for most other resources, and we're really not evolving how we're thinking about default energy bids for traditional NGR resources today, and we're more or less using that same paradigm for the ESR resources that we'll have in our market going forward that are also going to be subject to market power mitigation. So the third cost is opportunity cost. This is relevant in the real-time market. So obviously, if you've got a storage resource and it's a 4-hour battery or any use-limited or limited duration energy source, if prices are, say, $70 or $80 in the middle part of the day, but you know that prices are going to go up to $100 later in the day, and the 4 highest priced hours of the day are going to be at 100, you wouldn't want to discharge that resource early or force it to discharge when prices are, say, $50 or $60, because you know you could get those higher prices later in the day. So at that point, you're really thinking about the energy limitation of the resource and not so much about the cost to buy and cycling costs, if that opportunity cost is higher, and that's what's fine. And that's really only relevant in the real-time market. In the day-ahead market, the optimization looks over a full 24-hour period. So the optimization really does have sort of the wherewithal, if you will, to say, yeah, I know that these 4 hours are the lowest priced hours of the day. I know these 4 hours are the highest priced hours of the day. And I'm getting sort of the most bang for my buck in terms of storage resources and improving overall efficiency of the model, reducing overall costs by charging these resources at the lowest prices of the day and the highest prices of the day. And that is what we see coming out of the results of our day-ahead market. So these opportunity costs, number 3 here, are only effective in real time. So if we go on to the next slide, please. So as I noted, the ISO is proposing to keep the same general construct for the ESR model, and we're basically going to be using the same 3 components to calculate default energy bids for energy storage resources. So it'll be the same cost to buy energy, cost to cycle the resource, and then if we're in the real-time market, we will be thinking about some form of opportunity cost as well. The default energy bid will be applied for storage resources participating in the day-ahead market, and then we'll add opportunity cost in the real-time market. And then the real-time default energy bid for energy storage resources is going to have one new feature that isn't included for the NGR resources that we have today. There's going to be a feature that I'm calling here a sloped feature. So as the default energy bid for discharging energy moves left to right, like we've been seeing in some of these graphs, it's actually going to increase. And I'll show you how we're thinking about doing that in the next few slides. And then we had a few weeks ago a discussion with the Market Surveillance Committee. Again, this was sort of part of the ongoing discussions about mitigation for most resources, but specifically in these cases for storage resources. And they kind of pointed this out as like, you know, you don't need this additional slope feature in the real time, or I'm sorry, in the day-ahead market, because it's already inherently built in, because that market's doing that same cost minimization that we just talked about a second ago. Okay, next slide, please.
Before we go to the next examples, we do have 2 questions if you'd like to go ahead and let our stakeholders ask them before the examples.
Yeah, I think what I want to do is I want to get through these examples. I think that might help explain some of the questions. So let's go a few more slides, but I promise not to move on beyond market power mitigation before we at least answer a few of those questions. So here, you know, I did want to go through an example of this new feature for sloped bid curves. And I think, you know, as I was just discussing, we do want to include the 3 different components of the default energy bid that we've already constructed for the NGR resources. So cost to buy energy, marginal cost for cycling, or the opportunity cost, and we're looking at a maximum here. So it's either the maximum of that cost to buy or cycling cost, or the opportunity cost, whichever one is greater. And then the way that we would determine the slope of the default energy bid for the discharge portion of the bid curve for these energy storage resources would simply be, and again, this is what we're proposing now, and we realize this is the first time we've proposed it, so I think we are taking feedback on this. But we're thinking about just simply averaging the 4 highest hours of LMPs to determine the slope of the default energy bid. This might not be a terrific assumption because obviously a lot of days we might see one particular hour that's very, very high, and then other hours maybe are a little bit lower and a little bit more common, so it's more likely to kind of have 1 or maybe 2 outlier hours So this might not be the best example, and again, I think we would be amenable to thinking harder about this. In this particular case, let's just assume we've got 4 hours. They could all have the same prices. In this case, we're just assuming that we've got different prices. So let's assume they're $60, $70, $80, and $100. We look at the difference between the lowest price hour and the highest price hour is $40 per megawatt hour, 100 minus 60, and we divide that by the 4-hour time period, and we get a difference of $10 per megawatt hour. So essentially, we're going to slope our discharge portion of the bid curve by $10 per megawatt hour. So we can advance to the next slide, please. So what does this look like? So the leftmost point of our default energy bid curve would be that same function that we use for the default energy bid for NGR resources. In this particular case, we've generated a slope of $10 per megawatt hour, so we can see what that red diagonal line looks like. The black vertical lines correspond to the different segments of the bid curve that are actually submitted and bid in by the resource in the day-ahead market. And then, oh, excuse me. And then the, pardon me, I'm sorry. And then the horizontal red lines correspond to the default energy bid. So, and the way that we're calculating these horizontal lines are just the the intersection of the diagonal red line and the vertical dashed line. Excuse me. Okay, and so this is what our default energy bid set would look like. If we go on to the next slide, this sort of not sure what's caught in my throat, but this sort of looks like how it would be applied. So for example, let's say these green lines on the right pane represent actual bids for the resource. We construct the horizontal red lines, which are the default energy bids. If the green lines are what's actually bid, this resource could have its bids mitigated down to those red lines in the real-time market. So that is the last example that I had here. So let's pause a minute and take those questions.
We could go ahead and unmute Alva from Pacific Gas and Electric.
Hello, Gabe. This is Alva. 2 questions. One, one is more of a hope. I think given that this whole framework is based on the idea that there are real costs for some batteries at their extreme ranges, this does not seem to account for that at all. It's based entirely on market prices, and I would really encourage you, if you're implementing this model, to enable resources to justify their costs in the extreme parts of the range, because they may be very high actually, and it may not be a question of exercising market power. It may just be that they are really only willing to operate in those extreme parts of the range if there's a great deal of value to the system from it. And so you might be subverting your own aims by implementing it in this way. The other piece of it, just a question more, is how it seems that mitigation on the discharge rate curve, the discharge bid curve, could conflict with the charge bid curve. Would you anticipate any modifications being made to the charge bid curve if the discharge bid curve were mitigated, even if it were mitigated to where the 2 curves would cross over?
So yeah, just to kind of go back to your first point, Alva, I think I see what you're saying, and I think our idea, we certainly understand that if the resource cycles more, the costs are often higher. And I think we are willing, and this is the same stance that we took with the NGR model, I think we're willing to accept and bake those, highest level costs into the default energy bids for the storage resources. I see where you're going, where you're saying, hey, look, if we're thinking about a storage resource and it has a variable, it could operate anywhere from its minimum state of charge to its maximum state of charge, and we know that last little bit of energy is particularly valuable, I could sort of see thinking about maybe historical prices, extreme prices that could potentially emerge in the market. So, if we see $1,000 prices 2% of the time, then maybe it makes sense that if a 4-hour battery is sort of operating within its last 2% of state of charge, that it might have a very, very high default energy bid, because it might need to capture those $1,000 prices that could potentially emerge, that do emerge in a real-time market.
That's another approach. That sounds like a good one, actually. That sounds like a good approach. Sorry.
Sorry, what was that, Alba?
I just said that sounds like a good approach. I think that would certainly, I would be more comfortable with hearing that you were dealing with those extreme cases and looking at the extreme segments of the bid curve.
Yeah, and I think what we need to do, and we frankly have maybe not as much time as we might like to put that together, but we need to think hard about how to characterize that, and I don't know. I guess the specific, it's always challenging when you get down to putting pen to paper on the specific methodology you want to use, because that's where it gets challenging. So I think we're open to thinking about that, but we might want to. We certainly want to get input on this call and in written comments, but then we might want to rapidly work with stakeholders to think about how that could be constructed.
Great.
Okay, and then do you want to sort of just frame up that second part of your question again?
Yeah. Well, currently for NGR bids, if you were to mitigate the discharge portion down, potentially you would mitigate the charge part of the bid down as well, because it might be you might be willing to charge at a price that was above the default energy bid price.
Yep.
In this case, but that's because there's a single bid curve. Here you have two separate bid curves, and so I'm just wondering if you would be, if it didn't look like there's actually any rules associating the discharge bid curve and the charge bid curve, and if there weren't, then nothing would happen. But I was just wondering if you were thinking of doing anything in cases where you mitigated the discharge bid down to mitigate the charge bid down as well.
Yeah. So we are still thinking about applying market power mitigation to both the discharge and the charging portions of the bid curve. We're not planning to do any of this like sloped piece to the discharging portion of the bid curve. So that would just still be one number that's generated, and it would be generated the same way that it's generated for the NGR resources today.
You mean the charge?
But I think, yeah, and I think the nice thing about this model is that you do have this slope for the discharge portion of energy, so you would inherently have some additional leeway up above the discharge for up above the charging portions of the curve.
Okay, so you'd basically be would you be mitigating it down so that every segment was below the corresponding segment? Maybe we can just take this as a question. I'd like to know what the rules would be rather than going into the details right now.
Yeah, I think it actually, if we went to maybe the previous slide. Yeah, I think the way that we calculate the default energy bid today for the NGR resources is just sort of number one here on the left. It's the maximum of the energy cost plus the marginal cost or the opportunity cost, and that's what's set for the default energy bid for both the charging and the discharging portions of the bid curve. In this case, I think you'd have the same thing where the discharge portions of the bid curve would be set by this methodology. The charging portion of the default energy bid curve would just be set on the bottom left portion of this calculation, and it would essentially be flat across the entire range of operations.
Okay, maybe you can give just show an example of that in a drawing, but that sounds good. Thank you.
Yeah, I'll make a note of that. Thanks, Alva. I appreciate it. So maybe one or two more questions.
There is only one question in the chat from Tina Perazzi from PG&E. She asked about slide 23. Did you consider efficiency of the battery in reducing the discharge segments of the bid?
Yes, so that is included. So when the resource is charging, we should I believe this is specified in the paper, and we certainly specified it in the paper for ESDR 4, but it's not specifically listed out here. But when we're thinking about charging costs, we're also thinking about round-trip efficiency for the resource. So just because it costs you $20 or $20 per megawatt hour to charge the resource, and maybe you have a really low cycling cost, really low wear and tear on your battery, it's not just going to be $20 that you're going to need to make in order to discharge energy efficiently and profitably. You're going to want to make a little bit more than that because, for every 10 megawatt hours that you charge and put into the battery, perhaps you only have 8.5 megawatt hours to discharge. So those round-trip efficiencies are factored into the expected charging costs for the resource. But great question. Thanks for clarifying that. Any other questions, Brenda?
Yes, one more last question from Carrie Bentley. Your line is unmuted, Carrie.
Can you hear me now? Hello?
Yes, sound good.
Perfect. This is Carrie Bentley with the Western Power Trading Forum. Gabe, thank you so much for going through that. I'll note, unlike me, you never say or and you went through that very, very quickly. In fact, this whole presentation, I acknowledge lots of time constraints, and I understand we can't have all-day meetings on the phone, but it's been really fast, and I had a lot of questions that I'm not asking for time constraints. There are also questions and requests I put in my comments that were not responded to. Some pretty big questions that I think should be addressed before we move forward. And then I noted the next draft is supposed to be the draft final. And I don't want to tie up your meeting asking my questions, but if they're not going to be replied to from the written comments and I don't have time to ask them here, I would just ask, can we do another working group or something before the draft final so that you can get full feedback prior to the board? Thanks. And sorry, I know this is a weird time to ask this, but I'm pretty sure there's not going to be time for questions at the end of this call.
Yeah, I tend to agree. And, when I was putting the slide deck together, I was just thinking to myself, my God, this is a lot of material. It's really heavy. And I agree with you. We've spent a lot of time and we have a lot of meetings internally to think and work through this stuff. And then when we get and present it publicly, we don't have nearly as much time as we did to think through it and work through all the details internally. So let me take that back and see what I can do. But I like that idea, and I do think that there's some things that we can improve on. And, I will be the first to admit that, we went through all the comments and we took the, comments that we saw a lot of and repeatedly, and we tried to address those comments. And we looked at, and we did seriously consider every comment that we received, and some of them didn't, we did consider them, but some of them we didn't necessarily address in the written revised straw proposal. But I assure you, we did think about them internally. But I like the idea of having some more time to discuss maybe some of these thornier issues and walk through some of the examples that we talked about earlier. So I'll take that back, but I do appreciate the comment.
Okay, thank you.
One more question. Oh, Susan Schneider.
Hi. Hi, this is Susan Schneider, Phoenix Consulting. Can you hear me okay?
Yes.
Yeah, hi. I just wanted to sort of double down on Carrie's comments in a couple of ways. First of all, this has been sort of an ongoing problem with a lot of recent stakeholder initiatives with the CAISO where comments go in and you can assure us that you've received comments or you've thought about them, but there isn't any explicit document or way or mention in the proposals and then subsequent proposals addressing people's comments. And so when people make a comment and they don't see something reflected in the next version, they do not know if you have actually read the comment, have you understood what was said, and they don't understand why it's not in the next proposal. So this is not a problem only with this initiative. It's been a problem with several initiatives, and I really would encourage you either in a separate document, maybe in a matrix of stakeholder comments, or in the next iteration to say, well, these people said this, but here's why we didn't do that. And it would just be really helpful to understand, because then you just end up repeating yourself the next time because you have no idea if the comments were why they weren't accepted or what was, if they even were read. So, if you don't want to hear the same thing over and over again, it would really be good for you if you just responded to them the first time the comments were made, and then you won't be hopefully hearing them over and over, or perhaps you'll get just a better explanation next time. So I wanted to second that. Also, and I think, for some people who are, trying to play whack-a-mole with some of these, things like market power mitigation, I'm looking at the slide that's in front of us now. Most of the things on this slide are not labeled. And I know, this is not my particular area of expertise, but, what are the green lines? What are the red lines? What are the blue lines? And it would just be helpful when you put these out. I mean, it's great to have these examples, but it would be really helpful to understand the examples if you could label the things that are actually in the examples. And so that's just a separate request, but I think it would really help with understanding if I got the arrows or the mitigation. Okay, so now I can see that the red prices are the mitigated prices, the green prices are bid prices. I don't know, but it would just be helpful if you could label the diagrams that are provided just in a little bit more detail, so we don't have to try and guess.
Susan, yeah, thank you, and I do appreciate your comments there on, doing some sort of a stakeholder matrix. I've actually raised this to my management, and I think, so that comment and feedback has been passed on because I know you've made that comment in the past as well, and I do appreciate it. And I agree with you. I think that's something that the ISO could get better at overall in terms of how we operate and perform our stakeholder processes.
It does seem to have gotten worse lately, Gabe. It was sort of common practice before, or at least to mention it in the next iteration. But the Hybrid Resources Initiative, several others, it just seems to have kind of backslid. I know you guys are under a lot of pressure and there's a lot of stuff going on, but it just would be helpful.
Yeah, I'll continue to escalate that. So I do appreciate that comment. And then I think just because these specific examples were taken directly from the paper,
right.
Yeah, they didn't have a whole lot of labeling on them, and there was descriptions about the colors and things in the paper. But I take your point. In the slide deck, it might be helpful to have labels on them because you don't have all of that written verbiage right at your disposal. So yeah, thank you for that comment, Susan. Okay, we are doing pretty close to on time, with the caveat that these are heavy subjects, and this might be the first or an early time when some of the stakeholders have been looking at this, and I do appreciate that. So yeah, to the extent that you're able to digest some of these topics and think about them a little bit more and, provide written comments, provide documentation and feedback to me directly. I'm happy to continue to have dialogue on these topics. And I think like we talked about, we will see if we can potentially set up some kind of like a working group or something like that to work through some of the specific details on parts of this proposal. Let's move on to reliability enhancements. So unfortunately, I'd like to say, yeah, the rest of this presentation is kind of easy and we've gone through the hard parts, but that is just not the case. So this piece of the proposal, there are some changes, and some of this is review from the last time, but there are still a lot of components that the ISO is thinking about in terms of reliability and how we want to change rules for resources participating in the market. But I do think we have added some additional clarity in terms of questions that were asked in the last round of comments and provided some feedback. But again, a lot of these ideas are still evolving. There's still plenty of opportunities to, or there needs to be opportunities to continue to think about and evolve these proposals as we go forward. So the first thing, and this is a somewhat new idea, and we've actually spent a fair amount of time talking about this internally, and I was going through the documentation for the issue paper and some of the other discussions that we've had around storage, and we haven't really talked about this particular idea a lot. But one of the things that we do know is that when a storage resource gets awarded ancillary services in the day-ahead market, those awards don't necessarily, they don't impact the state of charge for that resource. So, for example, a storage resource may receive a dispatch for regulation up for multiple hours in a row, and it might not receive any corresponding energy awards during those same hours. And the way that our day-ahead market handles that today is, because it's a capacity award, it doesn't impact the state of charge of the resource. So if the resource is fully charged at the beginning of the day, receives those 4 hours of regulation up awards in the day-ahead market, but no energy awards, then the day-ahead market anticipates that that resource is still going to be fully charged at the end of that 4-hour period. Now, in practice, if that resource actually gets those awards for regulation up in the real-time market, and they're actually realized in the real-time market, it could be providing energy in response to AGC signals because it's on regulation in the upward direction, and because it's actually extending energy in response to AGC signals, it will be slightly discharged as time goes on, and eventually you could get to a point where the resource, in fact, runs out of state of charge, which obviously would not be optimal for the ISO. So, we've been looking and thinking about our day-ahead market, and, there's obviously some ability for the ISO to estimate what kinds of impact regulation awards have on storage resources. But unlike energy awards, we don't know for sure. If a storage resource receives an hour-long energy award to discharge 10 megawatts, we know for sure that that resource is going to have 10 megawatt hours less of energy than it had at the start of the hour if it's responding to those dispatch instructions perfectly in the real-time market. What we don't know, and what is less clear, is how much energy that resource is going to have at the end of the hour in real time if it actually receives those ancillary service awards, and what kind of changes in terms of state of charge that resource would actually experience. So one thing we've been thinking about is estimating what kinds of changes across the day typically impact storage resources when they do receive ancillary service awards, and perhaps those numbers are different across different hours of the day. So, early in the day, maybe a regulation up award doesn't impact state of charge as much as it does during the peak ramping hours in the afternoon, say. So we're thinking about looking at some of that data, and we may include some changes to how the day-ahead market thinks about and assigns state of charge in relationship or when storage resources are awarded ancillary services. I would note that the real-time market does optimize or re-optimize ancillary services in the 15-minute market. So even if a storage resource were awarded several hours of regulation up in the day-ahead market, in the real-time market, the ISO is looking at this, and if there isn't sufficient state of charge for the storage resource to provide that regulating service, we obviously could get that regulation from another resource on the system or potentially another storage resource that is charged up. But then there are those concerns about the day-ahead market not matching the real-time market and there being potential differences there. So that is something that we're thinking about. Obviously, we don't have a full built-out proposal on that here. Hopefully, we'll get comments. We'll internalize those comments. And then, if we do plan to move forward with a proposal, we'll have that in the draft final proposal, but we are thinking about that currently. So if we go on to the next slide, please. So this is more or less the same slide that we presented last time on ancillary services for storage resources, and it is a similar concern to what was outlined in the previous slide. So there could be a situation where storage resources, potentially run out of state of charge while they're operating in the real-time market, and operations, and this is specific to California ISO operators, have actually seen situations where these storage resources have ancillary service awards, hour after hour, and eventually they do, become depleted. And even though we might like to use those storage resources, we could potentially have AS shortages because of unavailability from particular storage resources. And this is something that's actually happened. So one of the things that we've included, and this was the same, the proposal really hasn't changed much from the initial straw proposal, but what we proposed is to limit upward and downward ancillary services to the discharging or charging resources capacity, and then to require that those resources have unencumbered energy bids in the opposite direction. So, for example, if a plus or minus 10 megawatt resource got an award for 10 megawatts of reg up, at the same time we would require that resource in the real-time market to have bids for discharging energy between minus 10 megawatts and 0 megawatts. Essentially what this means is if we see a storage resource that's providing reg up, and this would be our market optimization, get very close to 0 megawatt hours of state of charge, we could essentially send it an energy instruction to charge, and then we'd be able to charge the resource and then avoid any situations where we didn't have energy in the resource and it couldn't provide responses to ADC instructions. So that's what we're thinking about there. If we go on to the next topic, so this is another topic that really hasn't changed much from the previous proposal. We did include a few clarifications in the document in response to some of the questions and stakeholder feedback that we received, but we are currently looking hard and thinking hard about local reliability when you have, and there's already been instances where storage resources have been procured specifically for local concerns. And when you have those local concerns and you have storage, larger storage resources in those local areas, what can potentially happen is you're relying on those storage resources to be around and be charged in situations where if a contingency occurs, you may be needing the energy out of batteries over several hours. So you may need to charge the battery up and to have it just sit there for multiple hours so that it can be available in the event of contingency. So local studies, the ISO does a lot of this work today manually. A few of the questions that we got from stakeholder feedback and comments from the straw proposal was to ask about including these kind of constraints and pricing them in the market. So I think we didn't necessarily clarify this in the initial straw proposal, but here we have, and we're saying we want to explicitly price these resources and have these resources be charged and have them be charged as a part of our market outcome and not an independent action that either our operators or operation engineering team is taking to charge resources or to set aside additional capacity and make sure it's available in these local areas. It will be something that's optimized by the market. And then, you know, the market obviously can be very sophisticated about how it makes these decisions. So it's not an operator saying, oh, you know, we think we need this resource because typically on hot days we'd like to have it started up. It's a decision that's made by the market software, and it's weighing all the considerations from across the entire system and expected or anticipated loads and capacities for energy that can be imported into local areas when it's considering whether or not to commit and charge storage resources. So yeah, that's where we're at there. Again, this isn't a huge departure from where we were before. It's more of a clarification. So we get on to the next slide, and this is outlining exceptional dispatch authority that the ISO is intending to add. Again, this is new feature because of the proliferation of storage resources. Occasionally, you know, it could be for a local issue, it could be for a system issue, but the ISO operators may need to exceptionally dispatch storage resources to hold state of charge. You know, and you can think about, you know, we obviously just talked about the local concerns, but the system concerns could be something like, you know, the ISO knows that it's going to be a very, very hot day. It just wants to make sure that capacity is charged as much as possible, and it could issue exceptional dispatches to charge resources on those kinds of days. For, you know, and that would be for reliability purposes. And I think what we went through and we were careful about in the initial proposal was to talk about this authority and the fact that the ISO would have this authority. What we didn't do is really go into the details about how this authority would be compensated. We provided sort of a high-level sketch, and I think the more we've thought about that, we've sort of revamped our thinking about how we would want to compensate for exceptional dispatch. And I'm not completely sure we've landed on what we want to have finally, but we do have a specific example of how that compensation will work outlined here in these slides. So let's go on to the next slide and start thinking about how that compensation would work. So, you know, we heard the feedback on clarifying how the calculations would actually be performed, and we heard the feedback on providing specific examples. So that's what we're trying to do here. Essentially, you know, at the highest level, we're trying to come up with an opportunity cost-based approach to think about how much to compensate these resources. So the highest level, you know, the ISO is requiring a storage resource to hold a certain amount of stated charge, you know, and what that could potentially do is limit the storage resources' ability to participate in the day ahead of the real-time market, and to the extent that you know, there's a limit there, you know, the resource could be missing out on opportunities to discharge when prices are high, and may have to sell energy at later times in the day when prices are lower. So I think the question that we're asking is, what are the differences in those prices, and how do we compensate those resources? And then the question that the ISO has to think about and internalize are, well, we don't have infinite resources to do this calculation. What's a relatively simple way that we can calculate this opportunity cost, do the calculation even on days when we have potentially a lot of exceptional dispatches for storage resources, and apply it uniformly to all of our you know, resources that could be exceptionally dispatched, and then internalize that in our settlement system, which is already very complicated, in a relatively easy and straightforward way. So if we go on to the next slide, we thought about how we're actually going to do that. And what we're specifically proposing here in this paper is to do two separate counterfactual runs to determine what the opportunity cost should be. And the first run would be a profit maximizing energy schedule without any exceptional dispatches included. And then the second run would be a profit maximizing energy schedule while we were observing the exceptional dispatch. And the idea would be, and we're just thinking about energy here. We're not, I'm not introducing ancillary services. And, again, we're trying to make this as simple as possible so that it can be done in a relatively easy, straightforward way by the ISO systems and internalized in our settlement processes. So the counterfactuals, and this is how we're thinking about it right now, are going to be based on actual prices realized at the resource's location. So we'll take a stream of LMPs that were actually realized for the resource. Some of the comments that were mentioned last time we presented this and in the written comments said, well, if these storage resources were actually allowed to participate in the market and they were discharging, you might get a lower price because there's more supply in the supply stack, and you're explicitly restraining it when you're issuing these exceptional dispatches. I think the ISO is noting that, we agree with that statement, but calculating what those counterfactual prices are is not computationally possible at this time. We can do it for one specific interval. We might even be able to do it for 2 or 3 specific RTD intervals. But if you're talking about an exceptional dispatch that happens over multiple hours, it's not possible for our ISO system to perform counterfactual calculations and generate LMPs for resources over a long period of time where output from one market run would necessarily impact input for the next market run and sort of keep track of all of that information, say, okay, if the resource did discharge, we'd then see these prices, but then the SOC would be updated, and that new SOC would need to feed into the next iteration of the market run. We just don't have the facilities to do that at this time in a way that would get accurate prices. The time frame that we've thought about, and we've talked about a lot of different ideas here, but I think what we've landed on at this point is to use the period when the exceptional dispatch is in place. So it could be a very short exceptional dispatch, it could be a multi-hour exceptional dispatch, and then we'll add on some additional time after the exceptional dispatch, and that additional time will correspond to the duration of the battery. So if it's a 4-hour battery, we'd add an additional 4 hours of price streams to examine for that period. And I think with these simplifying assumptions, and again, these might not be our final set of simplifying assumptions, but I think with these simplifying assumptions, we are able to come up with a meaningful calculation and, do this in bulk and perform it on storage resources on our system. So if we go on to the next slide, I think we are getting to the example here. This is the same hypothetical resource we talked about earlier, so we don't need to spend a whole lot of time on it. It's got a Pmin of minus 25 megawatts, Pmax of plus 25 megawatts, and it's a 4-hour battery, so it's got a stated charge that ranges from 0 megawatt hours to 100 megawatt hours. In this example, we'll just assume, and this is the input that we're assuming for our calculations, that the resource initially has 80 megawatt hours of a stated charge, and the ISO operations room decides in real time to tell the resource to hold at least 75 megawatt hours of stated charge, and it's going to hold that stated charge for 1.5 hours. This is a somewhat arbitrary assumption. Obviously, the exceptional dispatch could have been for a value of stated charge higher than the resource currently has. It could have been for 80 megawatt hours exactly, or it could have been, potentially it could have been something lower. I think the situations where the operations team would actually dispatch to a lower level of state of charge and would actually realize it's probably less common because if you got 80 megawatt hours, there shouldn't be a huge need to exceptionally dispatch a resource to 75 megawatt hours. But nevertheless, I did want to use this as a specific example so that we could just see how the numbers worked in this particular case. We're also assuming that for this particular exceptional dispatch, the ISO is holding it for 1.5 hours. So maybe we're putting it in place at, I don't know, noon, and then at 1:30, the ISO removes the exceptional dispatch from the market. In this particular case, and I'm going to show you the next slide what an example looks like, but the resource optimally discharges, there it is, optimally discharges when prices are high early in the exceptional dispatch, but is prevented from doing so later in the exceptional dispatch. So yeah, let's go ahead to the next slide. Great anticipation there. So counterfactual number 1 is sort of represented in the middle set of columns. Counterfactual number 2 is represented in the rightmost set of columns. And then to make everybody's life a little bit easier, instead of doing 12 independent prices per hour, I've actually, and possibly this makes it more complicated, but what I've done is I've broken down and I've said, okay, let's just assume for each 30-minute block, RTD prices are identical for every 5-minute interval, so all 6 intervals within 30-minute blocks. What sort of results would come out of this? Obviously, as you're looking at, or if you are actually looking at realized RTD prices, this whole thing becomes more complicated, but for an example's sake and for ease of digestion of this first example, let's make these simplifying assumptions. So the exceptional dispatch is in place for hour 0.5, hour 1, hour 1.5, and then after that period, we said we're going to look at prices for 4 additional hours. So that's the duration of the resource. So we're looking at prices for intervals 2, hour 2, through hour 5.5. And you can see here, I tried to make this maybe semi-realistic. We are exceptionally dispatching the resource to hold state of charge. And the reason we're doing that is because we're anticipating, maybe some relatively tight conditions within a local area. And while we're, yep.
It's so boring and so badly explained.
Want a coffee?
I think somebody may not be on mute.
Well, this is Susan Schneider. I actually thought that you were muting us. Am I trying to put myself back on mute?
I am not aware. Brenda, how is that working?
I am not. My hand is not raised.
Okay.
Adam, can you please mute Susan? She shouldn't be on. Yeah, go ahead, Dave.
Okay. So sorry about that. So what we see here are relatively high prices for this particular resource during that period when it's exceptionally dispatched. In the first half hour, prices are $95. In the next half hour, prices are $300. The following half hour, prices are $300. And then prices go down after that. So ideally, and that is the column marked ideal megawatts under counterfactual number 1, this resource, if there were no exceptional dispatches issued, this resource would be scheduled to discharge 25 megawatts in the first 3 half-hour intervals. In the next half-hour interval, when prices are $75, it would actually be charged at minus 25 megawatts. You can see to the column to the left of the the ideal megawatts and to the right of the ideal megawatts are the stated charge, and you can see what the impact of the ideal dispatch would be on the stated charge before and after that stated charge is issued. So, for example, in the first half hour, if the resource receives a dispatch instruction or an ideal dispatch of 25 megawatts, the stated charge would reduce from the initial stated charge of 80 megawatt hours to 67.5 megawatt hours, and the hypothetical counterfactual revenue for that half hour would be $1,188. Similarly, on the right-hand side, counterfactual number 2, the resource in the first 3 intervals when the exceptional dispatch was in place would be restricted to no more than dispatching 10 megawatts or receiving a dispatch instruction of 10 megawatts during that time period. and it would choose to do so obviously when the prices were highest at $300. So you would see a dispatch of 10 megawatts during the first hour or the second interval, and that would reduce the state of charge from 80 to 75. And then during the exceptional dispatch period, the resource would be required to hold at least 75 megawatts during that whole time. And you can see from the column on the far right what the expected revenue from that second counterfactual would be. The total there would be $9,400. The total counterfactual revenue in the middle column from counterfactual number 1 would be $14,473. So this resource would receive an additional payment in terms of an opportunity cost for being held for this particular instance of an exceptional dispatch to hold state of charge of the difference between the $14,473 and $9,400. So I do agree and admit that that was quite a lot of material, and we'll pause here for any questions.
Alva from Pacific Gas and Electric will go first. Let's unmute Alva.
Thank you. Thank you, Brenda. Gabe, just a quick question going back to the ancillary services. You used the term unencumbered. I basically really like your idea of having energy bids in place that the operators can use when they need to for those conditions. But when I interpret unencumbered to mean that you would not be able to, potentially not be able to provide symmetric bids for regulation. And I think that would be a very bad idea. So I mean, you know, the degradation you're talking about happens even with sort of symmetric awards, and when they're not symmetric, it's just going to make it worse. So I didn't like hearing that word unencumbered, which I don't think was on the slides. But I think you should look more in the direction of just requiring that there be energy bids, which you could even use the default energy bids to serve that purpose, so that the operators can dispatch when they need to under those relatively rare circumstances, rather than building this into the business rules. So that's just my comment on that. I'll defer to others to ask other questions. Thank you.
No, okay, yeah, I'd like to explore that a little bit more actually, because I think you're saying exactly what we mean. You know, if you receive a regulation award in the upward direction, and you're, you know, let's just say a plus or minus 10 megawatt resource, and you receive a 10 megawatt award of regulation up, we would require bids for energy in the downward direction. So you'd need to have energy bids from negative 10 megawatts to 0 megawatts, and we wouldn't. I think you're right. We wouldn't allow downward regulation awards in that region at the same time.
Yeah, I have a problem with that.
Yeah. Okay. Now, I think what we're envisioning you could potentially do is you could have, you know, 5 megawatts of regulation up and 5 megawatts of regulation down, but then we'd still have the ability to dispatch the resource, you know, the additional 5 megawatts in the upward direction for energy, and additionally dispatch the resource 5 megawatts in the downward direction for energy, but we'd still have the ability to do that. If you allow the storage resources to have a 10 megawatt award for regulation up and a 10 megawatt award for regulation down, that's when we're getting into situations where the resource is fully depleted or fully charged, and then we really can't reliably, you know, rely on those storage resources to provide EAF.
Yeah, but I mean, well, first, I think if you have the capability to award lower, to give lower awards but symmetric awards, based on the bids, with essentially, whenever you awarded megawatts, you considered the opportunity cost of having to essentially reserve some energy for real time. That to me is more legitimate. It still has a cost, but at least it's not leading to solutions which are by their nature unsymmetric and really are undercutting your whole aim. So just I don't we can talk more about it later, and we'll think more about it too. But it doesn't seem like that's the right way to deal with a problem. It's almost, as I say, shooting yourself in the foot.
Okay, yeah, I do appreciate those comments, Alva. So, maybe I wonder if. Okay, well, yeah, let's continue to think about that.
Yeah,
and that could be something that we enhance the proposal with.
Mm-hmm.
Next, we have Hugh Zhang. Hugh, your line's unmuted. Please be sure to introduce yourself before speaking.
Hi, this is Hui from Smart. Can you hear me?
Yes.
Yes, we can.
Oh, great. Yeah, thank you, Gabe, for walking us through the examples. This is helpful. My question is in regard to the SOC constraint, the state of charge constraint. I recently had a conversation with one of our battery folks at SMUD, and I learned that there is a constraint on the state of charge. Basically, what that constraint is that the state of charge of the battery need to be within a certain range, let's say 40% to 60%, just a random number I threw out there, within a certain time frame. And usually that's 24 hours to 48 hours. And my concern is this constraint, if not modeled or if not modeled correctly, could potentially cause some negative reliability impact in real time. For example, the unit may not be able to follow the DOT if the battery protection is kicking in because it has too high or too low state of charge. I was wondering, is this something that ISO has considered or discussed? And if so, what would be the best practice to handle this type of constraint?
Yeah, as you're mentioning this, it seems concerning to me. I think a lot of the ISO models are predicated on the idea that the entire range, normal range of operations for resources is available for ISO dispatch. So if a resource has a certain Pmin and a Pmax and a certain min SOC and a max SOC, for the most part, and there are some exceptions, that the ISO is able to dispatch the resource within those ranges. So if you're saying maybe a resource has a range of operation between 0 megawatt hours and 100 megawatt hours, but it has to operate between 40 megawatt hours and 60 megawatt hours for a certain period of time for the day, I would be a little bit concerned about the underlying reasons of why. And I would think that, if this is being driven by like local concerns, I would hope that, some of these new reliability tools that we're thinking about implementing in our local markets, which I went through a few slides ago, would help with that. And then the market solution would actually say, oh, yeah, we know we're going to need these resources charged at this time, so don't discharge these resources below 40%. For these hours of the day, and hopefully that would be an outcome of the market solution. If this is an argument about, well, it costs me more to operate my resource outside of the range of 40 to 60%, I would tend to agree that is not something that we're modeling today, and that might be something we need to consider in the future. But we're not, aside from the ESR model and the ability to bid in charging and discharging prices at different levels across the horizon of state of charge, we're not really thinking about much beyond that, if that's something that you're suggesting.
Yeah, this is actually a constraint imposed from the vendor, and this could potentially invalidate the battery warranty if we're not within a certain range for too long. So this is not kind of directly related to cost, although indirectly it is related cost in a way or another. So yeah, I think this could be something to think about. I think both from the ISO and the market participant perspective on how to model a constraint like that. One thing I have in mind is, I'm not sure if it's applicable here, is to use similar concept of the ABC for other available balancing capacity. Have a higher P-mean and lower P-max for regular dispatch, but reserve reserve the lower P-mean, the capacity between lower P-mean and higher P-mean, and a lower P-max and higher P-max for available balancing capacity purpose that will be saved for the last resort before going infeasible in the market solution. This is just my suggestion that I have in mind. I don't know if it's applicable, but I would think that this is something that we all need to think about.
Yeah, okay. I'd certainly like to see that in the comments. And I would also, we worry a little bit about contractual costs being modeled in our market and not modeling physical. We prefer to model physical costs, not contractual costs. So if these are, if there's something physical about the cost, I think that would be the kind of thing that would be appropriate to model in, say, a default energy bid or a bid for the into the ISO's markets. If we're just thinking about a contractual cost, though, we might like to understand a little bit more why these constraints are in place in the first place. But let's leave that. I do appreciate the question. Let's leave it at that, and we'll continue to dialogue on that particular issue.
All right. Thank you, Gabe.
Yeah. Thanks for the comment.
Hi, Gabe. So we are running a little bit behind. So we do have approximately 6 individuals on the queue to ask questions. Would you like to go to Adam Swedley?
Let's do 1 or 2 more comments, and then we will move on to the co-located.
Okay. So let's unmute Adam, who is next, and then we will do Joshua after.
Hey, hi, Gabe. This is Adam Swadley from DMM. Hey, I just had a question for you. So I'm looking at this counterfactual example you put together, and the counterfactual, I think, assumes that the resource would always be dispatched at the time of this exceptional dispatch to hold a state of charge. So I guess what I'm struggling with a little bit here is I don't think I've heard any mention of how the counterfactual analysis would consider bid cost of the resource. So in other words, would it have even been economic based on the resource's submitted bids for it to be dispatched at a given time? And if not, are you still proposing that it would be compensated for some sort of opportunity cost?
So we will not be considering, or at least we're not planning to consider bids explicitly at this time. What we would consider, though, are things like round-trip efficiencies and the costs that were registered with the ISO for wear and tear on the resource when it's charging and discharging. So that would, if the resource would be uneconomic to charge and discharge because of those costs that would need to overcome, then I think what you're getting at is no, there wouldn't be any additional payments made because of the exceptional dispatch. But here, we're trying to make this as simple as possible. It's a full information problem, so it's not like you're guessing on what the prices could be and thinking about what the bids are and what prices are related to those. It's just what would you do if you knew what the prices were and you had the exceptional dispatch, and what would you do if you didn't know what the prices were, and comparing those two numbers.
Okay. Yeah, so I can appreciate the need to make some simplifications. I guess I'm thinking of a scenario where, say you have a battery that has a bid at the bid cap of $1,000, and the LMPs that you're looking at were $50. So in that case, the battery would not have been economic to discharge during that period of time, even without an exceptional dispatch to hold the state of charge. So I guess what I'm asking is, are you still proposing to compensate some kind of opportunity cost in that case, assuming that it would have been discharged, or would you consider the fact that based on the bids that the resource had at the time, it would not have been economic?
Well, I think the short answer is, well, I think it depends. One reason that a storage resource might be bidding high is because it knows or it anticipates higher prices later in the day. So I'm bidding $500 now because it's a super hot day and I'm expecting 4 hours of $500 prices, because that's what materialized in the day-ahead market later on. So in those cases, when we see higher prices after the exceptional dispatch, I think the idea would be that that this optimization that we've got would say, okay, you really wouldn't dispatch your resources right now. You dispatch them sometime later after the exceptional dispatch when prices were higher, and that would be captured by both counterfactual number 1 and counterfactual number 2. And as long as prices weren't, kind of like this example where they were high during the exceptional dispatch and then low later, you wouldn't really have an opportunity to recharge the resources. So the resource would be profit maximizing simply by discharging in those later hours in both counterfactual 1 and counterfactual 2. So you wouldn't get any additional payment there. But if those higher prices ever materialized, and they really did materialize during the periods when we had the exceptional dispatch, those would be the situations where we would be awarding the additional capacity payment.
Okay, so yeah, I think it's good that you're thinking in the direction of maybe what opportunity costs could be happening in future intervals, because it seems like a lot of the times when this situation might come about would be an exceptional dispatch to hold state of charge leading up to a period where the highest prices might actually be, rather than during the period where they might be. So, thank you for mentioning that. I guess, I didn't appreciate that the approach you were describing considered those types of situations. So that's good. I would still maybe want to think a little bit more about whether or not bid costs should be considered in making any kind of counterfactual based payment. So anyway, thanks for the clarification, Gabe.
Yeah, absolutely, Adam. And we welcome DMM's comments and everyone's comments on this. We realize this is sort of the first bite of the apple for how this payment for exceptional dispatch would work. So we may need to iterate on this in the draft final and final proposals. But I do appreciate those comments. I'm just looking at the time right now. I'm seeing it's 3:30. I know, Brenda, you mentioned we have a couple more callers in the queue, but why don't we move on to the co-located enhancements? Oh, yeah, go ahead.
Oh, no, we're good. They put their hands down, so you could go ahead.
Yeah, so we'll get through the co-located enhancements, and then if we have any questions on co-located, we'll take those, and then if we have any questions on any of the other topics that we've covered, which we likely do, we can circle back. Thank you for advancing the slide. Okay, so we've heard a lot of comments, and this slide is largely the same as what we presented last time about storage resources that are capturing investment tax credits or ITC credits, and concerns around property tax credits that storage resources may have to pay. And specifically, a lot of the language is around what's being referred to as quote-unquote grid charging. And essentially what grid charging is if you've got a storage resource and a solar resource at the same facility, and the storage resource is charging at a level that's higher than the amount of energy that's coming off of the on-site renewable at any time, that's what's considered energy that would be charging from the grid instead of energy charging from on-site renewables. We also realize that these ITC and property tax implications have manifested themselves in some of the contracts that have been struck between the storage resource developers and the off-takers of the energy from the storage resources. And some of those contracts explicitly prohibit having any period where the energy is flowing from the grid into the project and in these cases into the storage resource. And I think some facilities, and we've heard this with conversations from actual participants on the grid, have actually installed hardware that prevents energy from flowing from the grid into the project. Now, I think initially when the ISO was thinking about this issue, we were thinking about two potential models: a co-located model where you model the storage resource and the solar resource or other renewable resource independently, and a hybrid model where both resources were modeled as a single resource ID with a single bid curve. And in the case where the resources had concerns about ITC or property tax, and they had these sort of contractual limitations, they could potentially model themselves with a P-min of 0, which would effectively prevent net energy from ever flowing from the grid into the project facility. And that really is, with the way that the model is set up for storage resources, that really isn't possible with the co-located resources. What we've learned since then is that in addition to these challenges, that potential contracting challenges, there's also some challenges around using the hybrid model compared to the co-located model because of off-taker rights on the specific projects. Like, say, one off-taker has rights to the solar component and one off-taker has rights to the storage component, then the settlements for the solar and the storage really do need to be separate for some of these resources. So, sort of in that light, the ISO is willing to accept that a lot of these contracts were written before, even before the models were in place for storage resources, and they could have been written well before the models were in place for co-located and hybrid resources, which is relatively new. The ISO typically likes to, and we've discussed this a little bit, model actual physical parameters, operating characteristics, and physical limitations on resources, and prefers not to model contractual limitations because contractual limitations necessarily lead to less market efficiency. If we have access to the whole resource and we can optimize it with all the other resources in the market, we're going to get a better solution than if some of the resources are constrained because they're not able to operate during a specific range during a specific point in time. So, but because a lot of these contracts were put in place before the ISO had these models in place and before, frankly, a lot of storage was online in the system, we are willing to update and enhance some of our models to include these contractual limitations for a relatively short period. And what we're thinking about here is a specific set of limited circumstances when we would observe those contractual limitations. And really, the idea would be that they wouldn't apply to new resources that are coming onto the system after this policy is implemented. So if we advance to the next slide, please. What are those circumstances? So co-located resources, and this is what we're proposing, could potentially elect to impose or potential constraints, or we might actually dub this as a independent model from our co-located model that we have today. But essentially, these constraints would prevent them from ever having energy flow from the grid to the combined facility. We would, however, require that these resources provide documentation to the ISO in order to qualify for this model. So if you've got a contract that prevents you from grid charging, you need to show us documentation and provide information that says, hey, look, I'm really not allowed to grid charge because of this contract. The other thing that we want to make clear is that, we're allowing this, or we may allow this, if this gets approved, for certain resources with these constraints today, but we're not allowing this forever. This would be something that would be, that resources could potentially be eligible for up to a 5-year period from them joining the grid. and that's how long we understand that the ITC implications last for, but you wouldn't be eligible to receive the same treatment after that 5-year period. We also would note that not all resources would be eligible for this. If your resource comes online after this policy is implemented, we would expect that, similar to other resources and how we model typical resources, your physical operating capabilities, not the contractual capabilities, are what's going to be modeled in our master file going forward. And the ISO, this last sub-bullet is sort of just a note. The tariff does require all storage resources, and this is ISO policy, that when you receive a dispatch instruction, you're following that dispatch instruction. So if you're a storage resource and you've got a PMIN that's negative, and you receive a dispatch instruction from the ISO for a negative PMIN at your PMIN or at a negative value, even if there's energy coming off of your solar storage resource, and you're not registered under this new model, we do expect that resource follows your dispatch instruction. I would note here, and this is a conversation that we've had internally, that, similar to all policy, these rules have to be approved by FERC. So it's not just the ISO saying, yeah, we want to be nice and observe these contracts. FERC also has to sign off on this. So I just want to raise that as a potential concern, that, if this policy moves forward, it also has to be approved by FERC. And, once it's approved by FERC, then it would be implemented by the ISO. If we move on to the next slide, please. The ISO, so how is this going to work? Basically, we would allow these storage resources to observe contractual limitations, and I'm not necessarily saying all contractual limitations. Essentially, these would be the grid charging contractual limitations. And what we would do is, if this alternate model or these alternate constraints were implemented and the resource showed the ISO the necessary documentation and it was registered under this model, in those cases, our market software would automatically ensure that dispatch instructions for the storage resource would never be issued beyond the energy that's coming off of the renewable component of the co-located project. So if you had and when I say energy, I'm really thinking about the forecast energy. And this, for co-located resources, we could, it could be a plus or minus 10 megawatt resource, storage, and a 10 megawatt solar resource. And then the solar resource is anticipated to have, let's say, forecasted at 4 megawatts. In those cases, the on-site storage resource would never get a dispatch instruction to charge beyond 4 megawatts. So when we were working on our hybrid and co-located policy in the Hybrid Resources Initiative, we were thinking quite a bit about how to maximize the amount of generation that was coming from our storage resources, our renewable resources in co-located projects. And we recognized that occasionally there could be dispatches where energy would be, coming from the storage resource, and energy would be anticipated from the on-site solar, but potentially in real time, the on-site solar could generate additional excess energy. And we created rules for those co-located resources to back down from output off of the storage resource so that they could increase output from the on-site renewable resource. And by doing so, you could sort of maximize the total amount of energy from your renewable sources and, in theory, least cost sources on the grid, and acknowledging the fact that we know our forecasts aren't always perfectly going to match up with the actual amount of energy that comes off of these resources in the real-time market. So we're doing the same thing here. We recognize that, our forecasts aren't going to be perfect for the renewable resources, and that means that we might anticipate 4 megawatts coming off of the solar resource, but in actuality, only 3 or 2 megawatts might come off the solar resource, and that would mean that your storage resource could effectively back down from its scheduled charging amount if it, if it was 4 megawatts down to that 3 or 2 megawatts was actually coming off of the solar resource. Now, we wouldn't allow the storage resource to deviate beyond that point, so we wouldn't allow the storage resource to say, no, I just don't feel like charging this interval. They'd still be required to charge at the level of energy that's coming off of the storage resource, but they could back down, or the solar resource, but they could back down to that level. We are not changing our settlement system, so any deviations from the dispatch instructions would be settled as uninstructed deviation energy. This is exactly the same as the policy we put in place in the Hybrid Resources Initiative. And, there would be no specific ISO settlement measures between, say, the on-site solar and the on-site storage resource. That would be something that would need to be worked out contractually between the owners of the storage resource and the co-located renewables on site. Let's move to the next slide, please. So I think this is my last slide. Storage resources have requested additional functionality for how they're treated when they're pseudo-tied. Today, pseudo-tied resources must show transmission capacity for the full rating of the underlying components. So if you've got a 50 megawatt, plus or minus 50 megawatt storage component and a 100 megawatt solar component, and you wanted to pseudo-tie both of those resources to the ISO, you would need to show a full 150 megawatts of transmission between those resources and the ISO border. We are updating those rules to say, essentially the same rules that we have here if those two resources were located on the ISO grid. We would only require, if the resources only had 100 megawatts capacity, essentially that would be the upper limit of what we would dispatch the combined resources for. We would model that with the ACC, or the aggregate capability constraint that we already have in the market for co-located resources. The requirements that we have on these resources, if they are looking to pseudo-tie, is that they have to be located in the same balancing authority area. We couldn't take resource A that's located in balancing authority 1 and resource B that's located in balancing authority 2 and have those act as co-located resources that have to be in the same balancing authority area. And then we would use, and this is what I said before, we would use the aggregate capability constraint to limit the dispatch for the combined resources, and that would be essentially handled the same way that we handle co-located resources on our grid that are located within the California ISO. Okay, with that, I'd like to pause and just see if we have any questions on the co-located update, and then if we have time, we'll take questions on anything that we've covered today or any other storage matters that we haven't discussed.
Okay, let's pick on Susan Schneider to go first to ask questions on the co-located update.
Hi, Gabe. This is Susan. So I want to apologize, actually, for what happened before. I had no idea that I hadn't been muted, and I was actually talking to my husband about some tax document from our house and had absolutely nothing to do with you. So I do apologize if there was anything out there that was inappropriate, because I didn't know you guys were still listening. Anyway, so aside from that, I have several questions about this, and it's one of those things where I think your heart was in the right place, but the details just aren't not quite fully baked here yet. So if this applies only for you, if you go to one thing that would help, by the way, if you do number slides, if you go back a couple of slides, one more. Oh no, that's it. I'm sorry. Let's see, election pose. Yeah, that's it. Okay. So if the resources are eligible for 5 years from joining the grid, but here they're only eligible after the policy is implemented, I guess it's not really clear what exactly this is. Are they eligible for 5 years from when they begin operation? Is that their commercial operation? or if they join the system, if the policy is implemented, later this year, and then they join the grid, do they not get their 5 years, or what exactly did you mean to do here with the eligibility?
Yeah, and admittedly, I think this falls under the same category as some of the other things. This is really our first stab at, clarifying some of the rules around this. I think our idea would be that, we wouldn't, we understand that some resources, some storage resources do, to back up, I think most storage resources on the ISO grid that are co-located are trying to take advantage of ITC credits.
Yes,
and some of those resources have contracts that prevent them from grid charging, and some of those resources don't have contracts that prevent them from grid charging. Some of them are sort of saying, well, we know that we can charge from the grid a little bit as long as we don't go over this 25%. We'll be fine, and there might be some additional losses because of grid charging, but maybe we'll also be able to buy some really cheap energy in the middle of the night or something like that. So I think where the ISO would like to move is to a point where fewer resources are contracting with terms that say, hey, we can't grid charge with this resource. We want the resources to be available in the middle of the night if we absolutely positively have to exceptionally dispatch a resource to charge. And these tariff rules would prevent that. We could be in trouble. So I think what we want to do is encourage resources that are coming onto the system after this policy is in place to not have those terms that explicitly prevent grid charging in place. For the old resources, for the legacy resources, we understand, these contracts could have been struck years ago, and we will observe those.
Okay, but what you're saying is, first of all, that people are not doing this because they want to. People are doing this because they have to in order to finance these things. So saying it doesn't promote grid efficiency is, I think, a very limited view of grid efficiency, because many of these projects probably wouldn't be built at all if they didn't have the ITC. So it makes the grid much more efficient to enable these things to be built and to be usable to the grid. And so just looking at this one narrow thing and saying this is inefficient, yeah, okay. I mean, I understand you want complete flexibility, but I think it's just a very narrow perspective on ITC. No one's doing this because they want to. They're doing it because they have to. And so I think that's maybe one way to look at this. But the other is, so are you saying that because you understand that people don't sign contracts for 5 years, they sign contracts for much longer, and resources that that your 2016 bulletin had the ability for people to use limiting schemes, and this is sort of goes to our comments we've made twice now and asked for clarification. The Hybrid Resources Initiative, the metering sections had a limiting scheme in to prevent charging from the grid. Mentions those. We've asked about this twice. People are doing this because they have to, and once they come on, so are you saying that if they have a contract that's already been signed, that they can come on and have 5 years, or does everybody get 5 years once they come on, or do you have to? I guess it's just not. Even this one slide looks contradictory. It says you get it for a 5-year period from joining the grid, and then you get it. If you join the system after the policy is implemented, you don't get it. So your own slide is contradictory, and it was really hard to understand what you were trying to say here.
Okay, so there's a delineation between the universe of resources that are going to come online before this policy is implemented, and there's a universe of resources that are going to come online after this policy is implemented.
Okay, and come online means reach commercial operation. Is that what you're trying to?
Yeah.
Okay.
Yeah.
Okay.
Commercial operation. And those resources that come online after this policy is implemented, what we're proposing here is that they would not ever be eligible for this special treatment.
Okay, but what if they sign their contract? Again, contracts are signed years before a resource can come online. Usually it's maybe right after the phase 2 study or somewhere in the development stage. And so a resource coming online, say at the end of this year, which may be after you implement this policy, yep, still would have a contract that could require this element.
I think we might be somewhat flexible on this date, but I think that part of the point here is that the ISO does want to put a firm date in place that says for resources that are going to be commercially operational after a certain time, we're not going to observe these contractual limitations.
Okay, but if they still have, let's say they don't even have a PPA, if they still have ITC limitations financially, are you saying that won't count here?
So I absolutely think that resources that are approaching that 25% threshold should have higher default energy bids, and the ISO should not be dispatching those resources in a way that would be using up, their ability to get any ITC, so to fall off that 75% cliff from charging from on-site renewables. So I completely agree with that.
Well, does the resource get a higher default energy bid if they have ITC considerations? I don't think that's part of your proposal.
I would like to go back and look at what we included in the proposal for ESDR 4, which is, the basis of the default energy bids for the ESR model, which is what we're proposing here. But I do think that was specifically listed as something that could be included in default energy bids for storage resources.
Well, what about property taxes? Is that going to be a consideration here? I mean, it's mentioned in the proposal, but then it sort of gets dropped in this whole this part of it. Yeah,
I think that is an area where we could continue to dialogue on. But I think we're sort of in the same boat where we're saying, okay, we're for resources that have property tax implications on their dispatch instructions. We're willing to observe those for a 5-year period, but after that, the ISO is not willing to include this as part of our modeling.
Well, what if the ITC is extended, or what if the property taxes are still there after 5 years?
I think at that point we would need to look at new policy to address that. But, I think, taking a step back from the words that are on this slide, the idea is that the ISO, recognizes that storage resources are incredibly flexible. They're very valuable resources to have on our system. We want these resources participating in our market as much as possible. And we are concerned that if a large portion of our fleet and, every year as more and more resources join our market, if those resources have limitations on when they can be charged, it's going to become a greater and greater concern for us. So we would like to see fewer resources with these grid charging restrictions come online, and eventually all resources participate fully in our market with full capabilities to charge and discharge.
Okay, so if federal policy doesn't change, and if there's longer ITCs, or if property taxes are the way they are, the CAISO is going to say, I'm going to ignore that and just do what we want to, what we need to do or want to do here. It just seems odd that the CAISO is supposed to be accommodating, policymakers' decisions, and then to undermine them. I think your heart was in the right place here. We appreciate the fact that this is even here, but if it's in a way that it's not really usable for people, it's not really going to help. So, and if it's not clarified in terms of who was eligible and for how long, that's going to be a bit of an issue too.
Well, certainly every resource that's on our system right now that has these contractual issues would be eligible for this for for up to a 5-year period after they were commercially available on the system. So we're giving, that at least gives some runway for all of the storage capacity that's on our system, or the new storage capacity that's on our system right now. And this isn't saying that we couldn't ever reevaluate this policy, and maybe in 5 years we do look at it again. But I think this is just what we're suggesting right now.
Okay. Well, we would appreciate if you could, and I want to get off here because we only had 15 minutes, and I do want to give somebody else a chance to ask a question. But if you could look at the other alternative ideas we had, or in in the questions we've asked twice now in comments about things like, could you just set the ACC to 0 for co-located resources and do it that way? So we'd like to at least, have you respond to that if you could. And so you're gonna hear it again for the third time in our comments here, but it would be great if you could respond to them when you see it again.
Okay. And frankly, I think something like setting the ACC to 0 is like an implementation strategy on how we would, implement a policy like this. Because I think under the hood, that's essentially what we'd be saying is, yep, your output from resource A plus output from resource B can't ever be less than 0, that sort of thing.
Mm-hmm. Okay. All right. Well, anyway, thanks. If you could respond to that, that would be great, and I really do appreciate that. Let me get off here and let somebody else ask some questions.
Yep.
Thanks, Gabe.
No, Susan, I really do appreciate your comments and feedback on this, and I know you've been, one of the primary proponents to this part of the policy, so I do appreciate your questions. I'm looking at the clock right now, and I'm actually seeing that we have just 2 minutes left. So, Brenda, I might turn it back over to you to conclude, because I know you have a couple of important announcements. And then if there still are questions out there, I'd be happy to field those over email, and obviously you can email Brenda or our customer support team to get those answers resolved.
Of course, yes. I did receive a comment from Sean. We could definitely answer that offline, and Chris, feel free to message me right now on chat. But we do have less than 2 minutes to conclude this meeting. This next step for this energy enhancement initiative is, in order to hear everyone's comments, please submit them through the tool we have here available on Hyperlink, and also you can see it on the chat link provided. Please submit those by April 4th, 2022. And then also a Save the Date symposium for this year, November 9th through the 10th. We will be hosting it at the Safe Credit Union Convention Center in downtown Sacramento. Registration will open up on May 2022. A public notice has been issued, and if you do have any questions on that information, feel free to visit the webpage on Stakeholder Symposium, and then ask any questions to symposiumregistration@kaizo.com. So with 1 minute to conclude, Gabriel, thank you, Gabriel and George, for your participation in this call. We look forward to everyone's questions. Right now, we are going to conclude this meeting, and if you do have any questions, please submit them, and we will answer them as soon as possible. So now I'll go hand it back to my event producer to help conclude this meeting.
All right, thank you so much, Brenda. Ladies and gentlemen, this concludes our webinar. Thank you for using Event Services, and you may now disconnect.